Dr. Mandeep Singh Bakshi from the University of Wisconsin, Green Bay, USA. Dr. Bakshi's invaluable expertise in the field of nanomaterials and their biomedical applications will undoubtedly enrich this course and inspire all the participants. We are extremely grateful to you, sir, for accepting our invitation and gracing this event.
We have with us Dr. Rajiv Jindal, head of the department and one of the course coordinator of this GIAN program, along with other course coordinator, Dr. Jaspreet Kaur Rajput with us. We now invite all the dignitaries to come forward for the traditional lamp lighting ceremony. This sacred ritual is a tribute to Mother Saraswati, the revered goddess of knowledge.
We now invite Dr. Jaspreet Kaur Rajput, the course coordinator of this GIAN program, to deliver the welcome address and shed some light on the remarkable achievements of our esteemed expert, Dr. Mandeep Singh Bakshi.
A very good morning to everyone. It's indeed an honor and privilege to welcome you all to this exciting course on iron oxide nanoparticles for biomedical applications, fundamentals of bioapplicability under the prestigious GIAN initiative. At the onset, I would like to extend a warm and heartfelt welcome to our distinguished foreign expert Dr. Mandeep Singh Bakshi and dignitaries, participants. A special welcome goes to all the participants who have joined us from diverse academics, research and professional background. Your presence, participation and support are a testament to the importance of this course and its relevance to advancing research and education in this critical field. As we commence this enlightening journey, I am pleased to introduce our distinguished foreign expert, Dr. Mandeep Singh Bakshi, who has joined us to share his profound expertise and pioneering research in this fascinating field. Dr. Mandeep Singh Bakshi is Associate Professor in Department of Chemistry, University of Wisconsin, Green Bay, USA. He did PhD from Punjab University, Chandigarh in Inorganic Chemistry. He taught in Department of Chemistry, Acadia University, Nova Scotia and Wilfrid Laurier University, Ontario, before joining Department of Natural and Applied Sciences, University of Wisconsin, Green Bay, USA. His research is focused on interdisciplinary field of bio-nanomaterials, green and environmental sustainable chemistry with applications in real-world problems. With career spanning more than 3 decades, Dr. Bakshi has authored numerous research papers in high-impact journals and contributed to major advancement in the nanomaterials. In this course, Dr. Bakshi will guide us through a series of sessions covering topics ranging from synthesizing and characterizing iron oxide nanoparticles to their diverse medical applications. His insights, drawn from cutting-edge research and real-world applications, promise to enrich our understanding and inspire new ideas in this domain. We are deeply grateful to Dr. Bakshi for traveling to be with us and for generously sharing his knowledge and expertise. I am confident that his presence will greatly enhance the learning experience for all of us. Please extend a warm welcome to Dr. Bakshi and let us look forward to an engaging and intellectually stimulating exchange of ideas throughout this course. Thank you and welcome one and all once again to this remarkable event. I wish you all a fruitful and engaging course.
I now request Dr. Rajiv Jindal and Dr. Jaspreet Kaur Rajput to honor our esteemed foreign expert, Dr. Mandeep Singh Bakshi.
Now we will begin with our session, starting with lecture 1 on quantification of solute-solvent interactions by Dr. Mandeep Singh Bakshi.
Whiteboard का करा, whiteboard. देख लो जो सेटिंग करना है.
एक्सक्यूज मी सर उसमें भी लेक्चर कॉपी नहीं है।
Good morning, everybody. Thank you so much. Thank you so much for sparing your time, valuable time, to attend this course. And I'm really grateful to Dr. Jaspreet, Dr. Rajiv, and other faculty members who have helped us to organize this course. And we are also grateful to Human Resources of India, providing us financial resources to conduct this course. So the meaning of this course is to give you some light, or to explain some of the recent advances in the field of material science. Can you hear me up to the last one? Okay, okay.
You can come forward if you have some.
Yeah.
The last 10 students, they can come forward. We have set
So, yeah. I have planned this course through the series of lectures. Before arriving at the material chemistry or the applications of the material chemistry in terms of magnetic nanoparticle, we will begin with some of the fundamental aspects which are required in order to understand the course material. So, what we will be doing, today's lecture is slightly rigorous lecture. I have to cover 27 slides, I think, in just probably I have less than 50 minutes. So I'll be speeding up, and this whole lecture is focused on the fundamental of solution chemistry, because the solution chemistry is the most important branch in chemistry to understand how we can synthesize nanomaterial in the solution phase. Okay, so it's a quantification of solute-solvent interaction. When we have to synthesize any kind of nanomaterial, whether that could be gold nanoparticle, silver nanoparticle, with whom you are quite familiar with, and most of you are synthesizing them, it all starts with the solute-solvent interaction. It's a basic solution chemistry. So we know that when we have to deal with the solution chemistry, so we deal with the homogeneous solutions, and these are the fundamental aspects which we need to understand quantitatively, that is molarity and molality, apart from mass percent, ppm or ppb. But in this lecture, and particularly throughout this course, we will focus our attention on molarity, molality, and mole fraction. I don't need to explain it in that depth, but I will help you to recollect some of the fundamental aspects of these definitions. Then we have to understand the the molarity and molality. In chemistry, it is very important because it's a quantitative science. Chemistry is a quantitative science. So when we understand a definition, we go through a definition or a concept. We need to understand that how we can apply this concept quantitatively. Quantitative means that we need to arrive at some kind of numbers on the basis of which we can say that this property is going to be enhanced or reduced. So quantitative is we can measure that property quantitatively. So when we have to deal with these definitions, you have to keep in mind that the units are very, very important. If you can understand the units, you can understand the definition. Suppose if I say that how we can define the molarity. So molarity is basically moles of the solute. You can write mole with MOL or MOLE, both are correct terms, and divided by the volume of solution. It is not the solvent, it is the solution. Solution means solute plus the solvent. On the contrary, when we deal with molality, so molality, the only difference is again moles divided by the mass of solvent. Now, the most important thing is you know the definition of the mole. So when we have to write or understand the definition of the mole, it is the solute, mass of the solute divided by the formula mass. Right? And if I am going to place in both cases, so it is mass divided by formula mass, and here it is volume, and here it is the same way if I am bringing over there, so it is the mass. But in order to arrive at the units, you know that molarity is molar. Molar is a short form for mole per L, right? On the other hand, molality is mole per kilogram. Now how can we arrive at the units of mole per L? So what we will be doing actually, so it is mass in grams. Gram per mole is the units of the formula mass, and the volume here you will be taking because it is L, not ml. So therefore volume must be taken in L. If you are going to solve it, eventually it is mole per L. The same way over there. So if you are evaluating the units for mole per kg, right, and it is gram per mole divided by kilogram, and the same way you will be coming mole per kg. Now the obvious question is why we need to have two different definitions, right? So why can't we deal with the molarity only or the molality, and why we need to explain the two terms for the concentration of the solute in the solvent? The question is, it's altogether related to the fact that when we deal with the volume, I mean to say here it is the volume, it is temperature dependent. So volume is temperature dependent. Whereas when we deal with the mass, so then we can exclude the temperature dependence term. So in other words, what is the meaning for this? The meaning for this is when you have to measure or you have to deal with the experiments where you have to vary the temperature, it means that it is not advisable to use the concentration in molar units. Then you will be using the molality rather than molarity. But when you are dealing with a constant temperature, so then molarity is good enough in comparison to that of molality. It is much easier to measure the volume in comparison to the weight of the solute or the solvent. So therefore, the volume of the solvent when we are measuring in the volume of the solution we are going to measuring. So it is much easier in the case of molarity, and hence at constant temperature we can easily apply the definition of molarity in comparison to molality. This is the most important aspect that you have to keep in consideration. The reason is any kind of nanomaterial synthesis. So you have to prepare the solutions where you will be dissolving either the gold salt or the silver salt. So I mean to say that you must be very careful in terms of the concentration, which concentration units you are going to apply. So this is what I have explained over here, and suppose quantitatively when you have to perform any calculation, I mean to say if you see any kind of numerical problem here, you could see that you have a numerical problem. It's asking you if you dissolve a solute like camphor in ethanol, and it's 1.47 grams of camphor that is dissolved in 125 ml of ethanol, and density is provided. So how can you calculate the molarity and molality or molarity or the mole fraction? So again, so it is not a big deal when you have to calculate the molarity. Obviously now you have the mass of the solute, so that is 1.44 gram. So it's a 1.47 grams. You will be keeping it over here, and then you will be taking the formula mass, right? And volume, the total volume of the solution, obviously here it has been provided for ethanol, and that is not a problem. If you choose 125 ml as the volume of the solution, assuming that 1.47 grams is not going to significantly alter the volume, so therefore you can choose, but you have to choose here the L units, and therefore it's 125 L, right? And now when you are going to evaluate it, right, you will be having the correct value of the molarity. In terms of molality, then in order to arrive at the mass, so you have been provided with the volume and the density. So therefore what you will be doing, so density, it is mass over volume, right? So in order to calculate the mass, so density is in gram per ml, right? And volume is in ml. So therefore you can cancel, and eventually you will come the grams, and you have to convert this grams into kilogram, and this kilogram must be over here. So by plugging the value of the kilogram, you will be able to calculate the molality. So I have already performed the calculation. We don't need to go through that. The only my purpose is that how we can apply these definitions to a real problem. Okay, so regarding the mole fraction, so I'll take another 2 minutes before I come to this slide. So mole fraction, you know that suppose if we are dealing with a kind of a solution. So solution is solute plus solvent. Okay, and if we consider it 100%, right, and you could have the percentage of the solute from anywhere between 1% to all the way 99%. Okay, so in that way the definition reverts. As you are going to have more than 50% of the component, then that would be solvent, and the other one would be solute. So solute and solvent is not strictly designated terms for the solid substance or the liquid substance. It's the general definition. Anything which is greater in amount, whether volume or the solid mass, so that will be the solvent. Anything that is in smaller amount should be the solute. So the thing is here, on the basis of the solute and the solvent, we have the definition or the term we call fraction. So fraction in fact is what we say that if the amount of the solute is 10%, we know that the amount of the solvent is 90%. So we will say that this is in part, and if I take the total amount of this, that is 100%, So I say whole, that is the definition of a fraction. Now we have to apply this general definition on the mole fraction. It means that instead of the percentage, if we deal with, I'm coming back here, if I take moles of solute plus moles of solvent, and then the same formula I'm going to apply. So therefore, if I have to calculate the fraction, but the question is for whose fraction I'm talking about. If I'm talking about the fraction, suppose if I'm saying that fraction is, sometimes the people use f, but the correct way to apply the fraction is x. X is, in most of the textbook, it is the x term, that x is used for the fraction. So if I say that mole fraction of solute is moles of solute divided by the total mole, or I can say the moles of solute per plus solvent. So moles of solute plus moles of solvent. And suppose if you have to calculate the moles of the solvent, so then instead of moles of solute, you will be using moles of solvent. So why I am explaining these basic terms, the reason is because at some point when you are preparing the solutions for the synthesis of nanomaterials, you need these terms, and you have to be very clear that how you are going to use them and what is the meaning of these terms and how, in which respect you will be applying it. After that, there is another important aspect in solutions. In what way we can explain the solution of nanomaterials in aqueous or a non-aqueous phase? Somebody can ask you that it is not that traditional kind of a solute which can be dissolved in a solvent. You know, the nanoparticles are crystalline when you are dealing with the gold nanoparticle or the magnetic nanoparticle, which I'll be explaining after some time. They are crystalline nanoparticle. So if somebody asks you that it is basically a heterogeneous phase, it is not a homogeneous phase because the solid particle is suspended in the solution. Yes, absolutely. Conceptually, it is correct that the nanoparticle which is suspended in the solution, so it is not entirely dissolved in the solution. But can we term the suspension of the nanoparticle a solution? Absolutely. Because the definition of the solution is that one where a solute, which could be 1 or 2, is homogeneously dispersed throughout the bulk of the solution. That is the definition of the solution. So there it comes the term miscibility, immiscibility, insoluble, and the saturated solution. There is no issue with the sodium chloride, potassium chloride, sugar. You will be having a completely homogeneous solution. The miscibility is fine. There is no problem with the methanol, ethanol, and you will have a homogeneous solution from 0 to 100% mixing. But the problem arises when you have slightly a longer tail in the alcohol as you move from methanol, ethanol, propanol, butanol. So then it becomes the problem. It's not a complete miscibility. Miscibility term is being used when the components are entirely miscible, right from 0% to all the way to 100%, right? Immiscible, oil and water, where there is practically no possibility of the miscibility among the molecules. Insoluble, so you can say insoluble or miscibility. Actually, the term miscibility we use when we deal with the liquids. So insoluble when we deal with a solid, one component is solid, usually the solute, and the saturated is the saturated solution. This is very important. You have to keep in your mind that for the saturated solution, the term solubility, the definition of the solubility applies to the saturated solution, not to any concentration below that, right? So if somebody asks you that this is the solubility of sodium chloride in water, it means that he or she is referring to the fact that at this concentration, you are going to obtain a saturated solution at a particular temperature and pressure. So that is the meaning of the solubility. So anyway, coming back to our problem that actually I'm sorry, I'm running slightly fast because I have to cover so many slides. So, so So, coming back to the same question, should we call the nanoparticle solution a homogeneous solution or not? Absolutely, we can call, as long as you have the stable suspension and you have the constant value. Suppose for the gold nanoparticle, if your absorbance of the gold nanoparticle, the intensity, not the wavelength I am saying, the wavelength of the absorbance of the gold nanoparticle is 520 nanometer. With the concentration, that wavelength is not going to change. But with the amount, the intensity of that absorbance is going to change, right? So therefore, what I want to say that as long as the intensity of that absorbance remains constant with the passage of time, the solution is homogeneous, and you can say that it is a solution where gold nanoparticles are entirely suspended, and that is the requirement for any kind of application of nanomaterials in the liquid phase, whether that is aqueous or a non-aqueous phase. So you must have a homogeneous solution. So when we will be dealing with the application at that time, I'll explain that why we need a completely homogeneous solution of nanomaterials. So this thing you already know. Here from propanol to all the way hexanol or GIAN, if we keep on increasing the length of the hydrocarbon chain, right? So that is that reduces the solubility. Now, the question is that why it happens that the solubility of alcohol with the increase in the hydrocarbon chain that reduces. Because it has a direct relation with the solubility of the nanomaterial in the aqueous phase if you are dealing with the aqueous phase solution, right? So in the nanomaterials, it is not that straightforward the way we are going to explain it. This is very straightforward. Everybody learns this from the BSc, that why the higher alcohols are not soluble and miscible in the aqueous phase. But when we deal with this kind of solubility for the nanomaterial, it becomes much more complicated. So I'll explain that, I think, in the next lecture. Okay, so what happens here? Suppose if I'm saying it is much easier to understand if I'm going to explain it in terms of salt. Suppose if I am dealing with ammonium chloride. Okay, this is ammonium chloride in water, right? And for the time being, you just forgot about chloride, because the term which we are going to explain it over here, that has no relation with the chloride. It's a spectator ion and it's already soluble. So I have 4 hydrogen to make ammonium ion. If I replace one hydrogen, and by replacing one hydrogen, I add the hydrocarbon tail, right? When the ammonium ion is dissolved in water, it is completely soluble, there is no issue. But when I have to add some kind of hydrocarbon tail, now if somebody asks you, you know, this is the Lewis structure of water. So this is the Lewis structure of water, 104 is the angle, right? And it's a dipole, partial negatively charged, partial positive charge, right? And we can simply depict it by this kind of a cap, right? So it means that this is electronegative end of the dipole and electropositive. On the basis of this, how you are going to arrange it? Obviously, you are going to arrange it like this. Or what I am saying that it is in fact a blanket of hydrogen bonded water structure around the cation, and I can say that this is the hydration sphere of water. But the question is, how I am going to draw the hydrogen sphere of water over here? This is a problem, because here it is CH2, 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 obviously CH3 over here. Right? Now, so the thing is that this hydration sphere exists because of the ion dipole interaction. But those ion dipole interactions are not possible. This is entirely non-polar region. So there is a water structure breaking, the hydrogen bonding between the partial negative to partial positive end, partial negative to partial positive end, and partial negative to partial positive end, that when breaks, then the ion solvent interaction come in effect, right? Ion solvent interaction, when the dipole molecules, so they have to solubilize a ion, dipole molecules of water, they need to break the hydrogen bonding, then only the ion solvent interactions are going to be established. But the question is, how we are going to depict this? If I am going to depict it like this, right, now what should be the orientation of the water molecule? The orientation of the water molecule, suppose if I am saying like this, it is not like the proper order where the negative end is directed towards the positive end. That is not the case, but it's the orientation that helps to strengthen the hydrogen bonding. So here the hydrogen bonding is strengthened, right, and therefore the blanket of the hydrogen bonding which is created over here, that is much more stronger than the rest of the bulk of the water molecule, because the water molecule want to run away from the non-polar portion, right, polar portion, and they want to run away. But the problem is, because this part holds the molecule in the bulk, whereas this part feels uncomfortable and wants to move away. And this kind of competing two kind of competing forces which will decide the fate of the molecule. Should it be in the bulk solubilized, or should it be expelled from the aqueous phase? As the hydrocarbon chain becomes more and more longer, it means that magnitude of the surface area of this, or the magnitude of the non-polar interaction, will exceed the polar interaction. Eventually the non-polar interaction will push the molecule to the interface, and thereby insolubility arises. So that is the reason why as we keep on increasing the hydrocarbon tail, and why the molecule is becoming more and more insoluble. Now this has a direct relevance to the nanomaterial chemistry. So the question is, you don't have the hydrophobic or the hydrophilic environment in the nanomaterial because they are crystalline. So why some of the nanomaterials are completely water soluble, and why some of the nanomaterials are insoluble, that we will come when we deal with that part after a few lectures. So I here just wanted to establish the definition, right? And before going ahead, so do not hesitate to ask me any question, right? So please go ahead. So I'll give you a minute, and if you have any question, you can ask me before I go ahead. Okay. Solubility of solid, for the time being it is not that important, but I've included this slide to just explain, because we have different kinds of solid. So the crystalline solids, so they are not soluble in the aqueous phase. Now it's a very conflicting statement. So the nanomaterials are all crystalline solid. How we can say that? Then the nanomaterials are bulk soluble. So we will come to that part, and slowly. But for the time being, you just need to know that crystalline solid molecule here, diamond is crystalline, graphite is amorphous, right? And metals do not dissolve in water, and ionic solids. So most of the ionic solids are soluble, but there are several ionic salts which are not soluble. Now we come to the aqueous phase. You know the term sustainability. Suppose we have to apply the nanomaterials for the benefit of the humankind. the life survives in the aqueous phase. You see, we have the oceans of water, not methanol, ethanol, right? And likewise, our human body, the biochemical reaction in the human body, so they take place in the aqueous phase. All biochemical reaction in biology, which we are going to study, so they need the aqueous phase where obviously pH is the predominant condition in order to trigger those biochemical reactions. So it means that water is very, very important component for the nanomaterial application. So the kind of nanomaterial synthesis I'll be explaining, so that synthesis we are going to conduct in the aqueous phase entirely. So the synthesis of iron oxide nanomaterial as well as gold nanoparticles, silver nanoparticles, you will see most of the publications, they focus on in the aqueous phase. People do research in the non-aqueous phase, but most of the application of the nanomaterials, so they restrict to the aqueous phase. So we know that water is very important. So no doubt from the biological point of view, it is the medium where life originates and sustained. It's a highly polar solvent and bed geometry. And one very, very important question. If somebody asks you that what is the Lewis structure of carbon dioxide, you know that it's a linear, and the bond angle is 180 degree, and here the bond angle is, you have seen, 104 degree, right? And there are 3 atoms in carbon dioxide. In water also there are three atoms. But what compels carbon dioxide not to have the liquid state or the condensed phase, and what compels the water molecule to have the condensed phase? In this environment, we have plenty of carbon dioxide, but it is all together in the gaseous phase. Your oceans, freshwater lakes, so all are of water molecules, lakes, and you don't have any lake of carbon dioxide, right? So that is the uniqueness of the water, because despite having the much smaller size, just of 3 atoms arranged in a band structure, right? Just like that of a carbon dioxide. So this water molecule is extremely important, not only from the our survival point of view, sustainability point of view, but as a very good solvent. So this is all together because of the hydrogen bonding, because the hydrogen bonding which you see in water molecule, it is it doesn't exist in many of the molecules frequently available in our environment, which are having the 3 atom structure, right? So this hydrogen bonding keeps the water molecule in the condensed state, and that is the reason when we talk about the solubility. Solubility is the term when we apply it when there is reversibility between the solid solute, partitioning between the solid state to that of the saturated solution. So it means that if you keep on adding sodium chloride at a constant temperature in room and pressure, right, at some point you won't be able to dissolve any more amount of sodium chloride, that any added amount of sodium chloride will be settled down. So what is happening? It's not exactly the same crystal which are going to be settled down. It is exchange between the solution and the solid. The number of sodium chloride molecules which we are going to dissolve in water at the saturation point, it's saturated solution, exactly the same amount is going to be precipitated out. That is the definition of the solubility at constant temperature and pressure. Now, the best way is to understand any change in thermodynamics, you know that. So any change that is in terms of energetics. So you know the definition of enthalpy. So enthalpy is a very quantitative parameter that can right away helps us to understand if the heat is going to be consumed, if we are dealing with the heat energy. The heat is going to be consumed when a change is happening, or a heat is going to be released when a change is happening. So when it is consumed, it is endothermic. When it is released, it is exothermic. So we can also talk about the energetics of the nanomaterial, but the fundamental basis to understand the energetics, it's not just single step dissolution process of the energetics. It's a multi-step, as in the case of sodium chloride. When you add sodium chloride in water, in order to dissolve sodium chloride, first you have to break the crystal. Wherever you are going to add the energy, include the energy in any form, maybe a heat energy, right? So that is the endothermic process. The endothermic process means the enthalpy is positive. This is the y-axis, energy axis, you see over here. So it means that if I have to split the crystal into its constituting ions, right, and it means that I have to work against the lattice energy, that energy which holds the oppositely charged ions in the three-dimensional lattice. Okay, so that is the reason the delta H for the first step, did you see the first step? So that is positive. So if somebody asks you, if you are going to say somebody that when we dissolve sodium chloride, energy is released because it's an exothermic process. He or she may ask you, okay, I'm holding this water bottle, you add sodium chloride and you are saying energy is released, heat is released, I don't feel it, right? So it is the amount of energy that should be fair enough to be sensed by your touch senses. If the amount is too low, very, very small, you won't feel it, right? But when the energy is too high, obviously you see the warmth, right? But the question is, somebody can ask you, but you have to break the crystal. How you can see the energy is released? So then you have to come at this point, you have to explain this, that it's not just one-step process, it's a multi-step process. Energetics of a change, any change, whether physical or a chemical change, so it happens through multiple steps. And the final addition of all the steps will conclude if the change is endothermic or the exothermic. So how? The first step is endothermic. Now, as I told you that if I have to solubilize ion in the dipolar water medium, I have to break the hydrogen bonding. Again, because I am breaking the hydrogen bonding, I need to input the energy. Again, energy is required. So you see delta H2. Now, the length of the arrow, you see the length of the arrow? That corresponds to the amount of energy. So amount of energy that is consumed to break the crystal is much greater in comparison to amount of energy that requires to break the hydrogen bonding, right? But once you have broken the hydrogen bonding, right, now you see the water molecules are independently existing to solubilize the ion. So then, now you have independent ions ready to interact through the dipole ion type of interaction. Okay, and this change, this step is highly exothermic. The energy is going to be released from here to all the way here. So what is the conclusion? The conclusion is that that's this solubilization of sodium chloride in water. If I have to calculate the delta H of solubilization, it means that I have delta H1, delta H2 and delta H3. Now, what the phase diagram is saying? The phase diagram is saying that delta H is plus and delta H2 is also plus. It's endothermic, right? That is endothermic, but delta H3 is negative. So it means that negative delta H3. Now, it means that it is in fact the competition between the two endothermic or the exothermic amount of the energy is consumed or released. But whatsoever is greater in amount, that would decide if the change is endothermic or positive, endothermic or exothermic. So here we know that when we dissolve sodium chloride in water and the resulting delta H of the solution is negative. So it means that this term delta H3 is more predominant than delta H plus delta H2. You got my point?
Yes.
So this is the way we decide the enthalpy of, if it is applicable to the physical change, it's a physical change, right? It's a physical change. The physical change, the definition of the physical change is that the molecule of the solute or the solvent, when they are going to mix together, they are not going to alter their actual geometry. So water molecule remains bent before the dissolution. Water molecule remains bent after the dissolution. Sodium chloride is sodium and the chloride ions in the lattice or in the dissolved state. So if I'm going to heat it, evaporate water, sodium chloride will revert back into the lattice structure. So that is why it's a physical change. But when the molecular structure of any of the component is going to alter, that is a chemical change. So I mean to say that, so when you are dealing with the energetics, so make sure that you know all the 3 steps. So this is simply the solubility with respect to temperature. So you don't need to deeply understand it. So anything potassium nitrate increases with temperature, all of them, only that of the lithium sulfate. Now we are coming to the colligative properties. So colligative properties, you know, are the properties of the solvents which alter when we add certain amount of solute in it. So it has a direct relevance to that of the nanomaterial solutions. So when the nanomaterial solutions are going to be prepared, when the nanoparticles are there in the aqueous phase, so are they going to affect the properties of the solvent or the medium where they are going to be suspended? Absolutely. The way this is the case over here. So here we have the vapor pressure reduction, freezing point reduction, boiling point enhancement, and obviously osmotic pressure. So here I don't need to go through in any depth. So you see that when you are not adding the solute, the amount of the water molecule in the gaseous state that imposes the pressure by bombarding on the surface, that is known as the gaseous pressure of water molecule in the air just above the solution. But that gaseous pressure reduces when we add the solute. So it is, you see the yellow balls? So when we add the solute, the number of water molecules available to go up, that reduces and hence the vapor pressure of the solution decreases in comparison to that of the pure water. Mathematically, the mole fraction, I told you what is the meaning of the mole fraction over here, right? So the mole fraction of the solute decides how much amount of the gaseous pressure of the solution is. So greater the mole fraction, greater is the reduction in the gaseous pressure, because it's a fraction, you see, in the fraction amount. When you are multiplying any number with that of the fraction, the total value is going to fall, right? So that is the meaning for this. And here is, you can go through this because we are running out of time. So it's simple numerical problem. So you have the gaseous pressure of pure water, 4.4 kilopascal, and mole fraction you can calculate, multiply it, so that is the gaseous pressure of the solution. Boiling point, elevation. So we heat pure water. So what is the definition of the boiling point? The definition of the boiling point is when the gaseous pressure that is being produced over here, in more and more water molecules, when they reach above the solution, eventually they create the pressure that equalizes with that of the external pressure, that is 1 atmosphere, right? When that happens, that is the boiling point, and you see the bubbles coming out of the solution. But when you add the solute, the same thing happens as you see over here. So the solute restricts the displacement of water molecule to fly away in the air. The same thing happens. So therefore, the boiling point, in order to arrive at the boiling point, you need to heat more. That is why the boiling point elevation, right? And the freezing point, fall in the freezing point, obviously because you have the solute, so less amount of water is going into the solid state, and that is the depression in the freezing point. This is a very important phase diagram of water. Actually, I wanted to draw it, but I'm going to leave it. So the phase diagram, suppose if you are dealing with a solution at 1 atmosphere, when you increase the temperature, see over here, the temperature increases on the x-axis, and you keep the constant one atmosphere pressure as you have now in this room, right? And if you start with water that exists in the solid state, suppose if you see this is minus 20 degrees centigrade, obviously you are dealing with ice, you keep on increasing the temperature. Eventually what is happening, suppose if I'm coming over here, this is the melting point of water, right? So it means that this is 0 degrees centigrade, okay? And if I keep on further heating it, eventually this is the boiling point of water, that is the 100 degrees centigrade. So this line, just concentrate on this line for the time being. But when I'm performing the same experiment by adding certain amount of solute or the sodium chloride, so again I have the solid ice of the solution, sodium chloride and water at very low temperature. But you will see that the melting initially was helping over here, but now the melting requires much lower temperature, because at 0 degrees centigrade you won't see the formation of ice, right? So the formation of ice has been shifted to the lower temperature, that is the depression in the freezing point. And if I want to boil it, it is not boiling at 100 degrees centigrade. That was earlier I mentioned at this point. Now it is going to boil at a much higher temperature, that is the elevation in the boiling point. And likewise, this difference is the fall in the gaseous pressure. So I mean to say that, so hopefully I think this phase diagram is very popular and very common phase diagram, right? So you just try to understand that how temperature and pressure affect the aqueous solution, any kind of aqueous solution. So quantitatively you can provide the mathematical formulation delta F, that is the freezing point, depression, delta B, that is the boiling point, elevation. The formula remains the same, only the constant is going to change. Here you have the constant, freezing point constant, the value is already provided. This is the molality. Sometimes the molality term is being used as B, small b, so don't get confused what is the meaning of B. But now in modern IUPAC terminology, we use the term B. And I is the amount of ions produced. If you are dealing with sodium chloride, the value of I is 2. But if you are dealing with sugar solution, the value of I is 1. So we can apply quantitatively, calculate the freezing point, depression, or the elevation in the boiling point using the same formula for this solution. You have to calculate the molality. As I told you that you can calculate the molality by the mass of the solvent and calculating the moles. So you can calculate the moles by the amount of the solute provided, and you multiply the volume with that of the density. What is the density? Okay, it has been taken as 1. So density of the solution has been taken as 1. So it has been converted into kilogram over here, right? So, and by plugging the value for the constant, you will be able to calculate both the terms, delta F and delta F dF and F dV. Now the last one is the osmotic pressure. It's a very important term. So I'll take another 1 minute for this because it requires slightly. So for osmotic pressure, actually what is osmotic pressure? Osmosis, it is related to directly the osmosis. Osmosis is very common, the process which is commonly used in biology. So suppose if I have a beaker of water, right, and what I do, this is water, and what I do, I separate, I put the, what we call the semi-permeable membrane in that beaker of water, right, and here I have water molecules, water molecules, right? And here also have the water molecules, right? But in this side of the component, in the other side of the component, I add the solute. So obviously, the amount of the water molecule which is available for the hydrogen bonding is much more over here than over here, because some of the water molecule is associated with the solute particle or the solute molecules. Therefore, the effective amount of water reduces over here. So therefore, water molecules start moving from the left component to the right component. Okay. Now this semi-permeable membrane only allows the water molecules to move, not the ions or the solute molecule, right? So if I place the lead over here, which is movable lead, right? So before adding the solute, the lead is at the same level in both the components. But when after certain time water molecules move over here, this lead pushes to a greater volume. So you will see the volume of this side increases. Obviously, it decreases on this side, but the level of the lead, that is proportional to the external pressure. That is 1 atmosphere pressure you may use, right? It means that in order to bring back to the same level of the lead, I need to add extra pressure. This extra pressure is in order to bring back this, so that the flow of water molecule from left to right can be stopped. This only can be stopped if I have the pressure equal on both sides. This extra pressure is given with the pi Greek letter, that is known as osmotic pressure, right? So now this is the osmotic pressure when I bring back the lead to the same level, and this extra pressure is proportional to the amount of solute. Only R is the gas constant, temperature is constant where you are performing the experiment. So it means the osmotic pressure is only related to the concentration. So the greater the amount of concentration over here you will be adding for the solute, the greater should be the osmotic pressure. So this is the meaning for this, and you can also calculate the molar mass of the solute by rearranging the equation. So capital M is the molar mass. It is not the molar concentration, it is the formula mass, right? So this is the mass of the solute, gas constant, temperature, and osmotic pressure, and the volume. So here I have provided you just a minute. Yeah. Okay, so it is the last slide. So this is important, and you will have the direct relevance to the what we say material chemistry. How? You see over here, the question is asking you to calculate the formula mass of the solute. Aqueous solution contain 1 gram in 1 L of a derivative of detergent, sodium iodosulfate, NE1. Osmotic pressure of this solution at 25 degrees centigrade is provided this kilopascal. What is the molar mass of the solute, right? And you have already the equation which you have derived over here. You have the mass, that is 1 gram, gas constant you have substituted over here, temperature must be in Kelvin. You have to keep one thing in your mind, that whenever we are going to apply, you see the gas constant. The gas constant, though I need actually another lecture in order to completely define the definition of the gas constant, but in short, you should keep in your mind that gas constant, that is the constant for the ideal gas. Most of the cases we assume the non-ideal condition as the ideal condition, right? The gas constant helps us to convert the units to arrive at the required quantity, right? So without the gas constant, sometimes it becomes very complicated to arrive at the unit, but gas constant helps us to arrive at the units. You see over here, so therefore the gas constant is in Kelvin, is kilopascal, per mole per Kelvin. So therefore, you are not supposed to use the temperature over here in degree centigrade. In this way, you won't be able to cancel the units, and you won't be having the appropriate units of osmotic pressure. Right? You got my point. So therefore, when you have to deal with a numerical problem like this, you must pay your attention for the gas constant that is provided. Gas constant had different units for the different values, but you have to keep in your mind that which gas constant is provided in the numerical problem. If that is not provided, gas constant is required, so then you have to pick that gas constant which helps you to arrive at the required units. You got my point? This is very, very important. If the gas constant is provided, it's fine. If it's not provided, then how you have to choose? You have to choose that gas constant which can help you to cancel out the units, all other units which are not required, only the one that is required. Okay, so here what we are going to do, the formula mass of the solute is 287. It is asking you to calculate the formula mass of the polar part. This is the molecular structure of the dodecyl alcohol, right? It means that this entire molecule has a formula mass 287. But you know that how much long is the hydrocarbon chain is C12. You know the formula mass for C12 is 155 gram per mole. You subtract from the value you calculated. This should be the formula mass of the polar portion, but this is very, very contradictory. Carbon is 12, hydrogen 1, oxygen is 16. If you add them, you won't get 132, right? So what is the problem? There is no problem with the calculation. Where is the problem? The problem is that here we are talking about the dry portion of the polar part. This is including the water molecule because the polar portion is also including the hydration shell. So therefore that includes the water molecule. Those are associated with the polar portion. So this is the last slide, so I should conclude it now. This lecture was required because the lecture which we will go through, they required this fundamental understanding. So therefore, I thought to include the fundamental lecture so that it would be easier for you to understand the rest of the lecture. So in conclusion, so what we have learned, the nature of solution, determinants of the solubility, so how much soluble is and what are the driving forces as I talked about over here. Then the characteristic properties of the aqueous solution, those are particularly the all these osmotic pressure, depression, freezing point, elevation in boiling point. So they are the characteristic properties as well as the characteristic properties of the aqueous solution means where we talk about the solubilization, and the colligative properties where we talk about all other properties of the aqueous solution when solute is dissolved and how it is going to affect the solvent properties. So hope you have understood all the slides. Sorry about that, I have to run through and I had to cover so many slides. But if you have any question, please go ahead. Okay, then actually we are again coming back to the next lecture at the same place. So after I think 10 minutes. Right? Thank you so much.
घर से बना के लेके आते थे उसके लिए।
I would like to announce that the official inaugural ceremony of the GIAN course will be at 3:45 p.m. and there will be a group photograph at that time as well. So it is mandatory for all of you to be there. Thank you.
सर्फेक्टेंट वाला ना वो शायद मेरा ख्याल करो जो Okay, so we are going to start with the second lecture. What we have learned in the first lecture, the definitions and the solution properties, we are going to now see that how we can apply those concepts, those quantitative information when we have to begin with the synthesis and properties of the nanomaterials. Okay, so here it is micro heterogeneous aquaspace for nanomaterials. What is the meaning of this? Yeah, as I told you in the previous lecture, that the definition of the solution is where we could see the complete miscibility between solute and the solvent. Solute could be in the solid state or in the liquid state or the gaseous state. That is not any kind of the part of the definition. The solute could be any component which is in much smaller amount in comparison to the solvent. What is micro heterogeneous? Heterogeneous we know, homogeneous and heterogeneous. Solutions, clear solutions are homogeneous no matter which kind of solute you are going to add in a solvent. Heterogeneous is where the miscibility is not appropriate. That kind of a mixture is heterogeneous. For example, the simple example is oil in water. So oil in water, there is practically no miscibility, and we call it's a heterogeneous phase when if there are two components, so they are not miscible. What is the meaning of micro-heterogeneous? The micro-heterogeneous is it means that we are talking about we are dealing with a term or the solute in terms of the dimension. Here I would say that we are dealing with the solute in terms of particles. Now when we introduce the definition of a particle, so what is the dimension of the particle? Nature has provided us the eyesight or the naked eye can focus on certain object, on the object of a certain dimension. For example, that nature provides us the ability to see a single hair. But if you reduce the thickness of the hair, we won't be able to see that. If you pick that hair, which is much thinner than the normal hair, and put it in pure water, you won't be able to pinpoint that, right? So micro means I'm typically saying that I'm talking about the scale. So that is in terms of 10 to the power minus 6 of a meter. That is a micro. Nano 10 to the power minus 9. So in this way, here we will be talking about the solution that is being prepared by a heterogeneous, which is in fact a heterogeneous solution, but that heterogeneous solution looks to be homogeneous. So therefore, the conventional definition, now the next question is, can we apply the conventional definition? And to develop, I need to start from the materials which are being used. They may be from the materials which are being used. They may be made up of copper, silver, platinum, or any kind of oxide. So then that is the chemistry involved in order to produce those objects by using these kind of materials is known as the nanochemistry. Now, when the size of the object is in micrometer, you see mu stands for micro, 10 to the power minus 6. When the size is in micrometer, so your naked eye has the ability to see this. And obviously, as I told you, the hair, the thickness of the hair is from 10 to 20 microns. But the problem is, if you have the blood sample, whole blood sample, the size of the blood cell is from 4 to 10 or 4 to 8 microns. You won't be able to pinpoint the single blood cell. It means that naked eye is unable to pinpoint ability to see the objects is concerned. So that is the scale beyond 10 micron or maybe 20 micron. But nanotechnology deals with a scale. Rarely it goes to a micron. Most of the nanoparticles which are being used for environmental applications or for other kind of device formation, you may say, so they have the dimensions, at least one dimension, because you have x-axis, y-axis, or 3-dimension. After the 3-dimension, at least your 1 dimension must be in nanoscale. So suppose if we have a nano particle which is in the form of a filament or a kind of a ribbon, it means that out of the 3 dimensions, at least one must be in nano dimension. Either the thickness should be less than 1 micron, or the width should be 1 micron. Length cannot be less than 1 micron, so that is the definition of a ribbon. So that is the meaning of nanotechnology. And how we can use the different synthetic protocols of chemistry to apply in order to synthesize nanomaterials. Practically, we have 2 predominant approaches. One is top-down and bottom-up. What is the meaning of top-down? Top-down means we have a large amount of material whose nanoparticles we want to make, right? And we will grind it with something. We will use a mechanical force in order to convert the bigger size into a smaller size. That is a very crude way of producing nanomaterials. Usually, the top-down approach, usually it is not fruitful in producing the nanomaterials of the same dimensions and the size. So, therefore, it is not that popular. But the bottom-up approach is much popular, where we are using atoms. We control the synthesis of atom. We allow the atoms to fuse with one another, and we control their crystallization, nucleation, so that a particular shape and size of the object is being created. Thank you. So that is the way we allow the atoms to produce the nano object. That is, atoms, I mean to say that if we are dealing with the transition metal nanoparticle, gold, silver, platinum, or maybe the oxides, so then we are using atoms to produce the nanomaterials. But if we have the soft nanomaterials, soft nanoparticle means the particles of the polymers or any kind of carbohydrate, or we want to use the particles of proteins, I mean to say the bigger molecules, then we can use the molecules which are already dissolved in water. We convert them, we control their aggregation, and we convert into the nanoparticles. And so therefore, proteins molecule-wise nanocrystals. So eventually we produce the nanoparticle. So keep in your mind that there is a common term which we use, nanoparticle. When we say, if somebody say that, can we apply the term nanoparticle to any kind of nanoparticle, or it is restricted to gold, silver, platinum nanoparticle, or any kind of oxide nanoparticle? What if we have the aggregated aggregated entities of the soft materials like polymer. Should that be termed as the nanoparticle? Yes, absolutely. The nanoparticle is a common term that can be used for the particle which are being synthesized from the atoms of the transition atom, transition elements, or we may use any kind of molecules. So therefore, soft or hard. We then differentiate the nanoparticle in the category of soft and hard. Hard nanoparticles are crystalline. Protein or the carbohydrates, the polymer nanoparticles never be crystalline. So therefore, they are included in the soft nanoparticle category. How we can produce them? It is in fact, the synthesis is in fact the branch of chemistry. So therefore, any researchers who is working in the nanotechnology, he or she should have some sort of information of the synthesis process of the chemical reaction, that which kind of reaction he or she has to pick in order to synthesize the nanomaterial. So the basic chemistry is very important. The knowledge of the basic chemistry is very, very important. So here we begin with, I'm not showing the entire solution. Now you know the definition of the entire solution, right? So here I am talking about only the solute. You may say that I have intentionally excluded the solvent element, solvent part, that is the water molecule, and only trying to put my attention on the reaction which will help you to understand how to synthesize atom. There are two ways. Here is the reduction. You will be adding the electron. This plus refers to the addition, not the charge. When you add the electron to the cation, you will produce the atom. You remove the electron from the anion, you will produce the atom. Usually the first one is the most popular because you have plenty of common reducing agents. You can use them, right, to provide the electron. So therefore you can easily produce a new neutral atom. So I mean to say that if you are choosing to have the gold salt, gold chloride is the most convenient salt we can use to produce a gold nanoparticle. So gold is in oxidation state 3. If you provide 3 electrons by using any kind of reducing agent, this is a very strong reducing agent, sodium borohydride, but you can use the sodium citrate or ascorbic acid, or there are other weak reducing agents, so they will also serve the purpose. But the only difference is you have to be very careful that how you have to control the atoms in solution, because now the thing is that when the atoms are produced in the solution, there is no way to monitor them immediately because they are happening at a very rapid scale. Right? So therefore, at that point you have to control the crystallization to achieve the particle size for the nanoparticle. But how you can control that? A reducing agent can help you. If you are choosing a strong reducing agent, it will instantaneously convert all cations. If you are choosing cations, they will reducing agent will convert all cations into atom just as soon as you are going to add them. But if you are going to add the weak reducing agent is time dependent. So it will take time, right? But there is difference. When all atoms are produced at once, the nucleation will instantaneously begin among the all atoms. But if you are choosing slowly weak reducing agent, the nucleation is going to be diverted to the different route. So therefore you have to be careful in which route you have to follow, right? So usually what we do when we have to produce the nanoparticles of small dimensions, right, and then we choose the strong reducing agent, but when we have to control the size and to produce a certain shape of the nanoparticle, then we choose the weak reducing agent. So here we add the reducing agent and we produce the gold nanoparticle. Now you see that we have the gold nanoparticle. Here the fundamental definition of the dissolution of solute in solvent comes. You see now, this solution is clear clear and red in color. What is the meaning of clear? Clear means when you can see through the solution. That is the meaning of the clear solution, right? So turbid is when you cannot see through the solution. So when you see through the solution, it means that you have a homogeneous suspension, stable suspension. Stable will be, how much stable it is will decide on the shelf life. How long, if you keep it on for a longer period of time, eventually nanoparticle will settle down and again you will have the transparent solution. If you have to use this kind of a solution for some kind of application, right, so then you have to have the stable solutions, stable nanoparticle. It means that the shelf life should be for the extended period of time. Somebody asks you that how we can determine the stability of a gold nanoparticle solution. You will be saying that the stability of the gold nanoparticle solution depends on the nature of the stabilizer which you are going to use over here. You see, this is the stabilizer. Now you have already read about the term colloidal. So now this is colloidal solution. The microheterogeneous solution is in fact the colloidal solution. Colloidal solution where the particle dimension is between 1 nanometer to all the way up to 1000 nanometer, and if that is going to produce a homogeneous solution, we call a solution the colloidal solution. But there is a condition. You cannot prepare a colloidal solution without adding a stabilizer, because if you do not add the stabilizer, the reaction is going to produce, that is fine. You will see the red color. But the particle which you are going to produce, they are not that stable which you are expecting, right? So therefore, the stability of the colloids is very, very important in order to use the colloid for any kind of application. You have to keep in your mind that application part may consume time for 1 day, 1 week. I mean to say, suppose you have to use the gold nanoparticle for a particular kind of application. And usually, as soon as you have prepared the gold nanoparticle, you are not going to instantaneously use for that application. You may need some pause, some time interval. So therefore, that time interval could be few hours, or it could be few weeks. It means that your gold nanoparticle solution must be stable for that longer period of time, so that you can easily use it for a particular kind of application in order to see the reversibility. You got my point? You should have quantitatively you must see that that reproducibility you are going to achieve, that could only be achieved if your colloidal solution, gold nanoparticle solution, is stable enough. Okay, now how we can achieve the stability of a colloid? Here, this slide I have a typically, How we can achieve the stability of a colloid? The best way to achieve the stability of a colloid is to produce the electrical double layer on the surface of the particle. You might have heard about the electrical double layer in electrochemistry. Electrical double layer is being established on the surface of a particle when it's suspended in a liquid medium. That could be, usually it is aqueous phase. That makes more sense in comparison to the non-aqueous or polar solvents. Now, next question is, if we suppose add sodium chloride, would that be fine enough to create the stability over here, right? The stabilizing agent or the capping agent. Capping or the stabilizing, capping means that we are producing a blanket of a layer around the surface of the particle, so that that blanket of the molecule, so that can interact with the dipolar water medium, and that would produce an electrical double layer to provide the colloidal stability. Sodium chloride is not a stabilizer. In fact, sodium chloride, no doubt it is going to produce electrical double layer, but that electrical double layer is not having predominantly negative or predominantly positive charge, because the sodium ions, if the sodium ions are going to absorb on the surface, chloride ions are the counter ions, they are going to balance that charge. So therefore sodium chloride is in fact inducing the aggregation of the nanoparticle, hence we cannot use the sodium chloride. But on the other hand, we can use a surfactant. We can use a surfactant. Now, what is the meaning of a surfactant? Surfactant is the word that refers to the molecule which is active at the interface. So which is interface? It is air and water. So here you know the water, here it is air. So the surfactant is, now surfactant is a molecule who has the dual ability to interact with the polar and the non-polar. It's surface active. This is the polar part and this is the non-polar part, right? So you can see from the molecule structure of a surface active molecule, right? The non-polar part will not be we will not be able to introduce into the aqueous phase. So therefore you have only one way of the placement in the aqueous phase, that is only at the interface where the polar part is going to be immersed in the water phase and non-polar is going to be in the air. So this kind of ability a molecule is possessing to be active at the interface, that is known as surfactant. And the same thing is happening over here. This is the interface, it's the solid phase, it's the aqueous phase over here. So the polar part, because it's a transition metal, this is a free electron cloud, so the polar part positively charged head group, so that is interactive to the free electrons cloud, and hence there are electrostatic interaction. The non-polar tail cannot stay in the aqueous phase, so therefore there is another layer of the molecule that allows the non-polar interaction, and the polar head group remains suspended in the water molecule to interact with the water molecule through electrostatic interaction. This is a bilayer. This is a bilayer. Now this bilayer, you see now, this bilayer is charged. You see over here, this is the head group. So there are counter ions for this one is, because every surfactant, if you say that, if I say that this is positively charged surfactant, in fact all surfactants, they can be categorized in ionic, non-ionic or pseudo-ionic category, and most of the time for the stabilization we use the ionic surfactants. So if this is a cationic surfactant, so there must be chloride, bromide or any other anion that can be used as a counter ion. But the difference is here, the charge which you are going to see over here, that is much different the way the sodium ion is going to be absorbed over there, right? So therefore the absorption of the counter ion is not that effective here on the bilayer as much over there. So the stability, bilayer, which whatsoever the stability it is going to provide you, that is much more effective in comparison to the stabilizing ability that is being provided by the sodium ions. So this stability now, the bilayer stability helps to provide the colloidal stability and helps in the stabilization of the nanoparticle. Now it all depends on the nature of the surfactant you are going to choose for the stabilization. That will determine the shelf life of the nanoparticle solution. If the surfactant is a weak surfactant, weak means that, what is a weaker surfactant? Weaker surfactant is the polar part is predominantly more polar, but the non-polar part is less non-polar. So this part is predominantly polar, this part is less predominantly non-polar, that's a weaker surfactant. But if this is much more non-polar in comparison to polarity, this molecule has no other possibility except to arrange at the interface. So therefore you have to choose that which molecules surface active molecule you are choosing for the surface activity. Sometimes surfactant can also lead to the aggregation. I mean to say that it is all experience. So I cannot deliver a blanket statement where I can say that no, this surfactant will give you this much stability, that surfactant is going to provide much higher facility. Usually the double tail surfactants, they are much better stabilizer in comparison to the single tail conventional surfactant. Single tail conventional surfactant, sodium sulfate is the most common conventional surfactant you might have seen in your many lab experiments. Okay, so apart from this stability, you can also choose, if somebody asks you that this is the only kind of a molecule, how can we prove this, that there is really a bilayer? So now you see in advanced research, everybody as a researcher, suppose if you ask me, though for quantitative analysis you need the math, but I always prefer to use the technique or the protocols which require less kind of methodology, theoretical theories, but more direct evidence. So imaging techniques, that's why in material science, in material chemistry, imaging techniques are very, very important, right? Imaging techniques can give you direct evidence of the bilayer formation. Suppose if I don't have this image, it is very, very difficult for me to prove that there is indeed a bilayer, right? So I may use a different kind of theoretical methodology or theories based on the surface science or surface chemistry. But eventually, I still may not be able to convince 100% that there is really a bilayer formation. But if I have a real image, I can really prove that the length of, the thickness of this bilayer is 4 nanometer. It means that you will calculate the length of the tail this and length of the tail this, and obviously the size, add them, and you will see. And if it is close to this is the transmission electron microscope. So I have to say few words regarding to the imaging technique. Whenever you have to read or see or to understand the transmission electron microscopic image, the first thing is it is known as a TEM, transmission electron microscope. There is one in GNDU that is not working. We don't have a none here in NIT. There is one in Punjab University that is working, and I think there is one in Punjab Agriculture University, PAU. So it is not a camera photo. You have, everybody is having the cell phone. When you take the photograph, you are not having the scale. And from the photograph, by taking with your cell phone, you cannot make out that what is the height of a person whose photograph you are taking, what is the width of a person, you cannot make out because there is no scale bar. But in material science, when you are going to take the image through the transmission electron microscope, the best way to read the image is first attention, you must focus your attention on the scale bar. So this much length refers to 20 nanometer. It means by concentrating on this much length, you can just check the diameter of the particle. So you see that the diameter of the particle may be 25 to 30 nanometer, right? And you can precisely, on the basis of the scale, you can precisely calculate the length of the bilayer, the width of the bilayer, and then you can quantify that whatsoever the model you are predicting, you are proposing, so whether that can be proved with the imaging analysis. So it is not only just one particle you need to see. So all the particles should have this kind of a shell around the surface, to prove that there is indeed a bilayer formation. You got my point? You don't have to pick just one. It means all of the particles should be alike and they should have the same image. Okay, so this is the way we explain, and there is another way. If you are, as I told you, that it's not only the surfactants which we are going to use for the colloidal stabilization, you can also use the polymer. So our basically the requirement is, if somebody asks you that what is the concluding requirement in just one statement, what kind of stabilizer should be? You have to say stabilizer should be, the first aspect is surface active. If that stabilizer is not surface active, not all molecules are surface active, only surfactants are surface active, then what is the other condition, other requirement? You can say that if the molecule is not surface active, then the molecule must be amphiphilic. Must be amphiphilic. What is the meaning of amphiphilic? The molecule that is possessing the functional group which can interact with the non-polar part, non-polar entity, and the functional group which can interact with the polar entity. That is an amphiphilic molecule. So the polymers are amphiphilic. So you have to choose a amphiphilic molecule. So all water polymer, so water soluble polymer, so they are amphiphilic molecule. So any you can say the polymerical couples you choose, and polymerical codes, so they have plenty of hydroxyl group. They interact with the water molecule, but you will never see the polymerical alcohol is going to be absorbed at the interface, because the electrostatic interactions are so intense with the water molecule through the hydroxyl group that they will keep entire polymer in the aqueous bulk rather than at the interface. But that polymer certainly can absorb on the surface of the nanoparticle, right? And in this way, if all the nanoparticles are being coated with, or they have the surface absorbed polymer, so then the steric hindrances or configurational constraints will not allow the nanoparticle fusion. Now the question comes that how this shell, which is created by the polymer or by the surfactant, can help us to generate a stable colloidal solution. Now we are coming to another story. That is over here. You know the potential energy diagram? Everybody, when we start with the physical chemistry, thermodynamics, we always start with the potential energy diagram, right? So here we say that the potential energy is on the y-axis, and here we say that it is the distance among the interacting species. Suppose if we talk about the hydrogen molecule formation, suppose if somebody asks you that how the hydrogen molecule formation is occurring among the hydrogen atoms, you can say the best way to explain that, rather than any kind of synthetic process, you will be saying that it is the potential energy diagram. So this is the potential energy when it is zero, right? When the two hydrogen atoms are infinitely apart from one another. This hydrogen atom has no sense of the presence of another hydrogen atom. So therefore, the potential energy of interaction between the two atoms, two hydrogen atoms, is nil. So therefore, the potential energy means they have no sense that another hydrogen atom is present in the vicinity. But when they start coming closer to one another, the potential energy starts decreasing like this, right? Now the question is, you might be asking, what compels the potential energy to fall? The reason for that is the hydrogen atom has one proton, right? So, and there is the electron density of one electron. Likewise, the same is the story over here. So what is happening? The electron density of one hydrogen atom that interacts with the nucleus of another one, and likewise the electron density of another hydrogen atom interacts with the nucleus of the other. So that brings the one hydrogen atom closer to another one, and hence, because their energy stabilizes, because the potential energy attraction set in, and therefore the potential energy of the system falls, and that is why the potential energy keeps on decreasing. And at this point, potential energy starts increasing instantaneously. What is this point? Where the hydrogen covalent bond is established. This is the point where the maximum electrostatic interactions are established between the electron cloud of one atom with the nucleus and vice versa. Now what happens beyond that? We are decreasing the distance. This distance is decreasing. It means that I am saying that this is the distance that keeps you minimum potential energy. Now, but what happens beyond that? When we further decrease the distance, then this nucleus starts sensing the presence of another nucleus. You got my point? And then the repulsive interactions set in. As soon as the repulsive interactions set in, the system gets destabilized and potential energy instantaneously increases. Now, what is the meaning of this whole story? The meaning of this potential energy diagram is we are going to apply on the colloidal stability. I mean to say that I have produced one, you might consider a hydrogen atom, a particle as a hydrogen atom, and there is another one, right? So I want this particle must be away from the other particle. There must not be any kind of attractive interaction between the two particles. That is the colloidal stabilization. That is required for any kind of application in nanotechnology. You cannot use the nanoparticle for any application unless they are completely separately swimming in the water domain. You got my point? So without independent existence of the particle, you cannot use them for any kind of application. I'll explain that when I come to the application part. So you have to create the reaction conditions, solution conditions in such a manner that this particle should not merge with another particle like this, right? So therefore, we need not this kind of potential energy dip when the colloidal particles are interacting, but we need this place. We should have the much higher potential energy. So here is the potential energy of the interacting particle. It's the same diagram you see over here. This is governed by DLBO theory, so it's a very common theory. And the concluding part of this theory is V is not the volume, it's the interacting potential, total interacting potential. It's a theoretical concept. It's the combination of the electrostatic contribution and the non-electrostatic contribution. That is the contribution that is provided by the double layer, electrical double layer. So I'm talking about the electrical double layer that is being created by the colloidal surfactant molecules, and then the non-electrical, that's the water-wall interaction. You already know what is the definition of the water-wall interaction. So those interactions actually occurring between the non-polar entities. So here you see that if I choose the same way as the way I have explained over here, the two particles are interacting. If the two particles are going to merge, nanoparticles are going to merge, then you won't be having a solution like this. You cannot have a solution like this. Then as soon as you are going to prepare the gold nanoparticle solution, within 5-10 minutes or half an hour, all gold nanoparticles are settled because of the aggregation among the particles, right? And that is not a colloidal solution. And you cannot use them for any kind of application. But if you have to use them in any kind of application, you must have a stable solution. So the stable solution you can have only if there are repulsive interaction, not the attractive, but the repulsive interaction. So it means that this is the attractive interaction. The attractive interaction are because of the water wall interaction. Now, there is another confusing thing here. If somebody asks you that, okay, I understand the nanoparticle in the solution. So here I have a solution of the nanoparticle here I have one particle, I have another particle. Should this nanoparticle interact with this nanoparticle through the polar interaction or the non-polar interaction? I'll be saying that there are two contributions of the interactions, a polar and the non-polar. Then somebody can ask you, what is the origin of the polar interaction? Why this particle is going to interact with this one? No, first I should explain the non-polar interaction. Why this particle is going to interact with this through the van der Waals interaction, that is the non-polar interaction. Now, here is a problem. If somebody asks you, why we are standing on the surface of the planet, why can't we fly away? Then what should be the answer? Because of
Gravitational force.
gravitational force. Do you know the origin of the gravitational force? You know the origin of the magnetic field on the surface of the planet, right? You know the origin of the electric field. Because of that, we have the glowing of the bulb and the tube, right? Do you have the any information what causes the gravitational force? It is always the matter attracts the matter, right? So we still don't have a clear explanation why matter attracts the matter. That is because our modern science is still silent about that. We know the gravity is there because of the internal structure of the planet. Every planet has a gravitational pull that is proportional to the magnitude of the size of the planet, right? But we still do not know why matter attracts matter. The same definition applies over here. It means that we will say the matter attracts matter. Whenever they say matter attracts matter, then we will say it is the non-polar interactions are in action, right? When we have to say the electrostatic interaction, we have to prove that the positive electrostatic potential is going to interact with the negative electrostatic potential. Only then we can say that this is because of the electrostatic interaction. But here that is not the case. We cannot say that this is electropositive, this is electronegative. That is not the case, because both are of the same crystal, same atomic arrangement, same surface chemistry. So therefore that term cannot be applied over here. So therefore it is predominantly the non-polar interaction, and we have to, this is what over here, the non-polar interaction, you see the VA is a van der Waals interaction. If the van der Waals interaction apply, if they are in action, so then there is fall in the potential energy, and eventually the particles are going to merge, and it's not a stable colloidal solution. It means that the polar, now how the polar interactions are going to work? We are in fact producing the electric double layer over here. The charge on the surface is, if you are using cationic surfactant, the charge on the surface is partial positive delta, it's a smaller delta referring to the electrostatic potential, and the same charge is over here. When the same charge entities come close to each other, they start repelling one another. They are not going to attract. That is the stabilization. So this is the colloidal stabilization. So you have to say that in order to, this is a very important concept. You cannot have the stabilization without creating the charge on the surface of the nanoparticle, and the charge on the surface of the nanoparticle has to be created either by choosing the surface active molecule or by choosing a specific kind of a polymer that can produce the stability. That is the meaning of the stability of the colloids. So now there is another slightly confusing concept, which is there is another slightly confusing concept. What is that? You might have heard several times who are working in gold nanoparticle synthesis. Sometimes you see that when you synthesized gold and nanoparticle, and if I'm not dealing with any kind of electrostatic or non-electrostatic interactions among the particle, but still the particles are going to settle down. It means that we are ignoring the gravity, but you cannot ignore the gravity. Gravitational pull is if the gravitational pull is the matter attracts to matter, this attractive interactions are working among the particle, right? And then how can we ignore the attractive interaction applying between the nanoparticle and the earth, right? So earth and we are here because of the matter attracts to matter. So the same philosophy we are going to apply it over here. For example, I have a water solution, right? And now in this water solution, I have a stable colloids, gold and nanoparticle. The first question is, are they under the effect of gravity or not? Yes, absolutely. Every form of matter is under the effect of gravity, no matter how tiny, no matter how big that is. But the question is, when we have produced a stable colloid, as I explained in the previous slide, when we produce the stable colloids, then if we say that okay, the colloid is stable for several months, where is the gravitational pull? Now, should the gravity is working or not? How can you say that the gravity is not working on the solid particle? They are suspended in the solution, right? No, gravity is working. But then if the gravity is working, and then what is the opposing force to the gravity? You got my point? It means that gravity is still working. But the question is, which force allows the particle to keep swimming, suspended, and not responding to the gravity? Or that force is predominantly stronger than the gravitational pull? That is over here. Okay, so in order to go through, it's slightly complicated, but it's a very clear mathematical treatment. So here is a particle. This particle is the settlement of the particle under the gravitational pull is known as the displacement with respect to time, and this is the concluding equation. So I'm coming over here and I'll explain what's the meaning for this. The first thing is that the gravitational force is mass of the object multiplied by the gravity. The G is the gravitational pull, not the gravitational constant. It's the gravity and the gravitational constant. Both are the separate terms. So mass can be volume multiplied by the density of the particle, and this is the gravitational pull, right? And there is another force which is applying on the suspended particle, that is the buoyancy. So what is that? It is the mass of the water molecule and multiplied by the gravity. So again, mass can be the volume and the density of water. The third is the frictional force. What is that? Frictional drag. When the particle is going to suspend, I mean to say when the particle is going to settle under the effect of gravity, it is experiencing the frictional drag. So the three forces are going to apply when the particle is going to settle on the bottom. The first one, the force due to gravity. Second one, buoyancy, and the third one, it is the gravity. The third one is the friction. And the frictional force, you see that it is the viscous drag. That is the frictional coefficient. So it's 6 pi. Eta is the viscosity, r is the radius of the particle, dx over dt. Now, if you take all the three equations and all the three components equal to 0, if you have to keep the particle suspended, right? Now you see that this is negative and this is negative. The reason is the gravitational force is pulling, but these two forces, they are working against the pull. Buoyancy wants to keep the particles suspended, and then the friction again wants to keep the particles suspended, and it's opposing to that of the gravity. That is why you have the negative sign. If you plug the values for all of them, eventually you come to this equation. This is the rate of the settlement of the particle under the effect of gravitational pull, and you see over here, density of the particle minus density of the water. Greater the density difference, greater is the displacement under the effect of the gravitational pull. Greater the radius, greater is the displacement under the gravitational pull. But what is opposing? Opposing, you see the viscous drag. If the viscous drag, it means that if the medium is more viscous, right, so it will oppose the settlement of the particle at the bottom. But where is the viscous drag? Viscosity of the water is constant. Viscosity of the water is constant. We know what is the viscosity. But how the viscous drag can be imposed, that is what here I have explained. The viscous drag, where we talk about the electrical double layer. The stronger the electrical double layer or the surfactant which we are going to use, the stronger are the electrostatic interaction with the water molecule, and that is enhancing the viscous drag or the frictional forces, and they are opposing the settlement of the particle. It means that if you have to prepare the stable colloidal solution, you have to be very careful that you have to enhance the frictional drag and the viscosity of the medium by putting an effective electrical double layer, and that will allow the nanoparticle to keep floating in the solution, and that is a stable colloidal solution. Everybody understands? Any question? Okay, I'll take another 5 to 7 minutes, so I'll try to conclude it. Okay, now there is another aspect. If we have to use the nanoparticle for a typical kind of a device, we have to control the shape of the nanoparticle. For example, if somebody asks you, okay, I have very small cell phone or any other instrument, and I have very tiny parts of that device. So that tiny parts of the device are composed of nanomaterial of specific shape and size. Among them, the wires are very important. Ribbons of the wires are very, very important in order to put them in the form of small parts of our device. How they can be synthesized? Chemistry. So we, as I told you that when we use the sodium borohydride to produce the atoms instantaneously nucleate into the nucleating entities. This is a nucleating center, in fact, where certain number of atoms are going to aggregate, maybe 100, 200, 600, something like that. So it's a small crystal, very tiny crystal, and it has a specific planes. So if you look at the inorganic chemistry and you talk about the crystal structure, so you know that for any crystal, so there are 3 kinds of crystal plane: 100, 110, and 111, according to the 3 dimensions in which direction the crystal grows. Right. So on the basis of that, you have 3 crystal planes. By manipulating, by passivating, by blocking certain crystal planes, suppose if I want to grow this nucleating center into a ribbon or a wire, I have to block the other crystal planes and only allow the growth to be hampered over here. So you see that the crystal plane, this one, it's 001 and 001, you can see over here, or 111, so they are being blocked. And only this crystal plane, so that is 110, and only the nucleation is happening on this one blocked by placing the surfactant molecules and allow the crystallization to happen like this. So this is I mean to say, suppose if you ask me in a very simple language that how can we do it, I say that it is the research and the experience when you will keep on going through or synthesizing the nanoparticle and slowly manipulating with the surfactant. Eventually you will come to know that how you can produce the spherical nanoparticle, how you can produce the hexagonal nanoparticle, how you can produce the rod-shaped nanoparticle or the wire-shaped ribbon shape. So in this way you can produce the wire-shaped nanoparticle, and here they are. How? And this what we developed. You see, these are the transmission electron microscope where we use the same kind of methodology. It's a seed growth method. Initially we produce a very tiny crystals of gold nanoparticles, spherical shape, all spherical shape. We reuse them in the second step to produce a rod-like nanoparticle, and we again continue with the synthesis by manipulating with the concentration of the surfactant, by blocking the crystal planes, and eventually we come to the nanoribbons or nanowires. And I think in next few lectures I'll explain that from in which devices or in which applications you will be using the nanowires. Okay, then apart from this, you should have, it's not only the wire, but sometimes self-assembled nanoparticles, so they are also required. Right? Again, I am using a different kind of surfactant. So here, these are biologically active surfactants. These are the lipids, phospholipid molecules. They are also surface active molecules, but they are much more hydrophobic, non-polar in comparison to the conventional surfactant. So I mean to say that you have to manipulate with a different kind of a molecule so that you have the nanoparticle arranged in chains like this, right? And it's a one-dimensional structure. If you do not want to have the nanowire, because the nanowire is a crystalline which runs from one side to another side, but this is the one-dimensional assembly of the nanoparticle. Suppose if you ask me what is the meaning for this, it acts as a sensor. When the nanoparticles are separately dispersed, I mean to say over here, it has a different way it absorbs, it interacts with the electromagnetic current. But when the nanoparticles in one-dimensional or in aggregated state, so then it has a different way of interacting with the wavefront or electromagnetic radiation. So that will be a kind of a sensing technique to apply for some kind of a technique. So, okay. Actually, I forgot that why I added this micelle formation, but I'll explain it in the next lecture, that how the micelles are formed. Okay, self-assemblies can also be achieved by using polymers. Here it is the block polymer, right? So, and then here you have the redox chemistry in action. I'll say you have to choose a polymer which can be used for the redox reaction. I mean, here you have the ether oxygens, so they can supply the electrons to the gold ion, and in this way it can convert into the gold nanoparticle. In fact, this reaction is happening in the micelles. It's a polymeric micelle. It's a micelle of a polymer. So let me just in one minute, I should explain you what is the meaning of this. It's a polyethylene oxide, polypropylene oxide, and polyethylene oxide. It's a very common polymer which is frequently used in all cosmetics. So what happens when it aggregates? It aggregates in the form of this structure, right? So this part is the PPO, polypropylene oxide. This side is PPO and PPO. You see a cavity formation, and this cavity in fact triggers a reduction reaction. So I mean to say, when the gold ions, so they come in this cavity, they get reduced by adding 3 electrons, and the gold atom is produced, right? So the kind of a reaction was shown over there. The gold nanoparticles are produced then in the cavity. So it means that in the cavity you have the gold nanoparticle, because you have created the atoms in the cavity, so you will create the gold nanoparticle. But how do you know that this reaction has happened? How do you know this reaction actually occurs? So then again I'll say the microscopic imaging. You see the micelles? The micelles are only the spheres, but the dark dots, you see the dark dots? They are the gold nanoparticle which I have shown over here. So they are over here. So all dark dots, so they are, you see in the scanning electron microscope, where you could see clearly the gold nanoparticle. You can prove them by what we call EDS analysis. So it is, I mean, say it's a scanning analysis where we allow the high intensity radiations and ejection of the valence electron take place. With the help of that, we can prove that the electrons which are being ejected, they are indeed ejected from the gold atoms or the gold nanoparticles. So that is the way to prove this. So I mean to say that there are different ways to produce the self-assemblies or a specific shape. So coming back again to just remind you that we first talk about the stabilization of the gold nanoparticle, then we talk about producing the nanomers or the nanoribbon, and then we talk about producing one-dimensional self-assembled structures like this, and then we talk about the self-assembled structure where we could have the growth of the nanoparticle in the micelles. So all these structures, so they have the applications which we will talk about after some time. I'm not going to explain all the application, but I'll take just few examples. Okay, so now actually, yeah, I am just last slide. And another, this is very important. Suppose if somebody asks you that what is the best way for a student in a college where there is no instrumentation available to see that if the what kind of gold nanoparticle of specific shape we have produced, then the UV visible spectroscopy that is available everywhere. I think now this instrument is available in high schools as well, right? So we can simply use that instrument to, for the time being, we can check if the gold nanoparticles are produced and which kind of dimension we are expecting. Qualitatively, we can on the shape of the UV absorbance, we can just at least we can have some idea that what kind of the shape of the particle is. So you see over here the UV spectrum, so slightly that is complicated, so I'm going to explain it in 1 minute. So this is the UV spectrum, absorbance and the wavelength in nanometer, right? So for a red color gold nanoparticle suspension, the one which I showed in the first few slides, so you should have the absorbance something like this, and this should be close to 520 nanometer. If you have the absorbance of that solution, red color solution, close to this, it means that you are having somewhere polyhedral nanoparticle dimensions from anywhere 5 to 200 nanometer, right? If this absorbance gets broader, the peak gets broader. It means the shape changes from sphere to some other like triangle or some plate-like or a bigger molecule of a different dimension. That is, if the peak is going to be a broader peak or slightly shifted, blue shifted, red shifted. But if you have the absorbance like this, wavelength nanometer, if you have absorbance at much red shifted, instead of here it was 520 nanometer, right, and this is more than 650 nanometer, it means you have only rods. It is very hard to get the rods, only rods. Usually the solution contains a smaller amount of the spherical particle. It means that you will have a smaller peak over here, sorry, just a minute. So you have a smaller peak over here, right, and for the spherical particles, right, at 520 nanometer, and a larger peak over here, and that is what we do. So if you have only this peak close to 520, it means you have only polyhedral particles. But if you have double peak, the one is over here, another one is over here, it means that you have rods as well as the polyhedral particle. But if this peak is shifted more and more, red shifted, it means that the size of the rod increases. You see, when it is close to 700, the size is this. When it is close to 820, the size increases, length increases, sorry about that. The length correctly is known as the aspect ratio. The aspect ratio increases, right? And here you see that if it is further shifted to red, close to the near IR, right? So the length further increases. So I mean to say, this is the simple way you can test what kind of nanoparticles you have synthesized and what should be the tentative shape. If it is only one kind of shape, you should have only one kind of absorbance. If you have the mixture of different particles, you have the different shapes. But this particular peak will only appear if you have the rods. If your solution is not containing the rod, this peak will not appear, right? So in this way you can just test your gold nanoparticle synthesis, and eventually nanotechnology is scientific modern times with significant implication in all walks of life. Implication, I am taking it slightly in a negative sense, toxicity, but I have not yet explained the toxicity. We will be talking about when we will be explaining the bioapplicability. Prevention is the best healthcare. Nanoscopic detection is the key to the prevention. Sorry, I should have included some more conclusion that how we can stabilize the nanoparticle and what are the characteristic feature for the stabilization. So you may consider that as well. So anyway, so we conclude this, and yeah, we are slightly 10 minutes above our the normal lecture time, but you are most welcome to ask me a question. Thank you so much for your attention. Go ahead, please. Go ahead. Don't hesitate.
Could you throw some light on the core cell synthesis? In the micellar synthesis of nanoparticles.
Yeah, that will be in the that is coming, I think.
Because you can control the particle size.
Exactly. Yeah. So that when I'll be explaining first the micellar system, means a surfactant and surfactant property, how the micelles are formed, how the micelles are going to change shape, and how that shape is going to alter the dimensions of the nanoparticle. Yes, please.
Sir, as you said that we may use fatty acid as a substitute. So we may use amino acid which have a polar and non-polar
Amino acids are zwitterionic molecules, right? So zwitterionic molecules are usually not surface active. They are not amphiphilic unless you are going to add a known polar functional group. So there are zwitterionic surfactants. So it means that you will be using derivatives of amino acids which are surface active. It means the amino acids which you are talking about, the 20 amino acids, probably they are not good. Some people use some of the amino acids. You may predominantly non-polar amino acids can be used, but they are not going to produce a very stable colloidal system. They can be used, means I mean to say when you look through the paper published, you will see the amino acids can be divided into polar, non-polar categories. So non-polar amino acids, predominantly non-polar, all of them are water soluble most of the time, so you have to use that. Okay, thank you so much. See you in the next session.
Thank you, sir, for such informative lectures. Now, our next tutorial will be at 1:30 at Department of Chemistry.
And boiling point elevation lab experiment. It is related to the first chapter, the first lecture, which we completed. Here, we will try to understand that how the colligative properties, in fact, can be evaluated experimentally. So therefore, we have picked just a simplest experiment, that is elevation in boiling point and depression in the freezing point. You will be doing the depression in freezing point lab experiment rather than the elevation in the boiling point, because the elevation in boiling point is time consuming. So therefore, in 2 hours time, so we thought that you could conduct just one experiment, that is the depression in the freezing point. What we have to do over here, in order to evaluate the depression in freezing point, I mean to say that it is simply that how much amount of the solute you are going to add in pure water. With respect to that, the freezing point is going to depress. I mean to say that it will decrease below 0. You know that at room temperature, at 1 atmosphere, the freezing point of water is 0 degrees centigrade. So, and that is for the pure water. When we add certain amount of solute, so then the freezing point will be lower than 0. Obviously, it will be the negative centigrade, and that should be proportional to the concentration of the solute we are going to add. So, what we will be doing? So, we need these components. First, you have to weigh the empty test tube. You can take a big test tube that can accommodate 20 grams of deionized water. Take the empty test tube, you weigh it on the weighing machine, then you will be adding 12 ml, close to 12 ml, and you will see that because the density of water is close to 1, and you have to get around 20 grams of deionized water. So when you are measuring 20 grams, you are not supposed to exactly have the 12 grams. So the nearest accurate value of the weighing machine to the 12, that is fine. It's 12.5, 12.56, something like that. And then you will be adding 1 gram of glycerol. You will see that deionized water is in the liquid state, and the glycerol, that is also in the semi-solid form. It is highly dense solute, so it is a transparent solute, and it is usually the glycerine which you commonly use in your household items. After that, you have to prepare the solution. This is the first solution you will be preparing by adding 1 gram, and then you will be preparing series of solution, about 8 solutions. In the next one, again you will be taking close to 12 grams of water, and then you will be adding 1.4, 1.8. In this way, you will prepare the 8 solutions. Once you have prepared the 8 solutions, then you have to follow these steps. What you have to do, you will obviously, because you have to see the precipitation in terms of the freezing point, so therefore you have to clamp it So clamp the test tube where you could see just in front of you on the stand. Then prepare a cold water bath by taking water, rock salt, ice in 600 ml of beaker. Actually, in order to freeze the glycerol plus water solution, you won't be able to freeze it in simple ice. So you will be using a cold water bath with the minimum temperature of -8 degrees centigrade. So by adding the salt and combination of all them, so just make sure that you have close to -8 degrees centigrade temperature for the water bath. Because of the presence of the salt, the water will remain in the fluid state. Water is not going to freeze at -8 because you have already added the salt in this. Place the test tube, which you have 8 solutions. So you may add if the bath is wide enough, bigger enough, so you can accommodate all the 8 tubes at once. Otherwise, one by one. Then insert a thermometer in the solution. When the mixture becomes thick slurry, remove the test tube from the ice bath. Thick slurry means it is turbid, cloudy, so you have to watch it. So when it is going to get turbid solution, you have to note down the temperature. Remove the test tube from the ice bath. Begin stirring. Okay, so you have to begin stirring to melt it. Melt the ice crystal. Dip the test tube in the room temperature. So you have another water bath that is placed at room temperature. So you are taking out the test tube from the cold water bath that is placed at -8 degrees centigrade and placing it in the water bath that is at the room temperature, that has obviously higher temperature in comparison to the cold water bath. So when you are going to, okay, so this should be immediately as soon as you are going to replace it from the cold water bath, immediately you are going to dip it, place it in the water bath that is placed at room temperature. Now you are stirring it slowly. Stir the contents of the test tube gently using the thermometer. So make sure that you are slowly using thermometer as a stirrer. Otherwise, if you're going to hit the thermometer hard to the walls of the test tube, you may break the thermometer. And then you have to record the temperature, which one? At which the last crystal has melted. Slowly you will see the turbid solution which you have got. So when you have placed the test tube at the room temperature, the turbidity is slowly going to vanish. And you have to note down the temperature where the entire turbidity is going to be vanished. The last sign of the turbidity, at the last sign of the turbidity, you will note down the temperature. Right. The temperature of the solution, because you will be adding the thermometer in the test tube, not the temperature of the water thermostat bath that is already at the room temperature. So what you have done now, you have to prepare 2 tables. One is the mass of the empty test tube. You have 8 solutions. Mass of the test tube with the grams of the water. Obviously you may have 12.1 gram, 12.3 or 4, something like that. And then you have the total mass of the test tube plus water plus glycerol, and then that is the delta T. So delta T is the temperature where you have the melting that is occurring, the melting in comparison to that of the 0 degree centigrade. So that is in the absence of the solute, and in the presence of the solute, the difference in the temperature is delta T. Now we have the delta T with respect to the solutions which we have prepared, but now we need the exact concentration. So you have water in grams, you convert in grams into kilograms. Mass so the mass of the glycerol, that is solute in grams. So therefore you have to calculate molality. You remember that I talked about in the morning that in order to calculate molality, so water is the solvent, and you have to take the solvent in kilogram. So glycerol is solute, so you will be calculating moles of the solute. In order to calculate moles of solute, so it is gram divided by the formula mass of water, solute. That will give you the moles of solute, that is glycerol, divided by the mass of the solvent. It's not mass of the entire solution. That is the definition of molality. So it is the mass of the pure water, and here you don't need the density because you are accurately weighing pure water. So therefore, whatsoever the mass is, you will be converting into kilogram. Eventually, you will be calculating molality, and you have delta T. You have already calculated. You have to apply this equation. So the freezing in the depression, you will be calculating for each solution. So you have each solution. So you will be calculating the delta T for the depression in freezing for each one. You have the molality for the each solution, each solution you have calculated over here. You will be plugging the value for the molality over here, and Kf, that is the depression in freezing point constant, that you can check it from my slides where have I already provided the value for this. I, what should be the value of I? Can anybody tell me? Just 1 minute. What should be the value of I for glycerol? 1, 2, 3 or 0? If you correctly understood the first lecture, the definition of the freezing point depression or the elevation in the boiling point, and if you have correctly understood the formula, the mathematical formula for the definition, then you must know what is the value of I. The value of I is a Wand-Hat factor. It means that how many particles are produced, how many particles, solute particles are produced. For sodium chloride, each sodium chloride particle splits into 2 ions. Each sodium chloride provides 2 particles. So therefore the value of I for sodium chloride is 2. For glycerol, glycerol is not going to, it's non-electrolyte, it's not going to split into ions. So therefore 1 molecule of glycerol is going to provide 1 particle of glycerol. So therefore the value of I is 1 over here in all the cases. So therefore Kf is constant, I is constant, you need simply the molality, and that would give you the delta. We have already calculated delta T from the experiment. We will be calculating the Kf. So where B is the molality, Kf is the freezing point depression constant of the solvent, and what we will be doing, so we will be calculating, in order to prove the definition, we will be calculating Kf. How we are going to calculate? We are going to calculate delta T, depression in the freezing point, that is in degree centigrade, against the molality, that is moles per kilogram, and depression in freezing point, so you are having molality, so you will be having a linear variation. When you are going to fit the linear variation, because you have 8 points when you are going to fit, the slope is in fact the Kf. So your slope is Kf, and you are calculating the freezing point depression and try to see if you have the correct value and how much it deviates from the correct value. From there you can calculate the error, the percentage error or the error in the measurement, uncertainty of the error in the measurement. So this is the experiment. So you have 8 points, just let me 1, 2, 3, 4, 5, 6, 7, 8, like this. This is the freezing point depression, and I can simply explain the elevation in the boiling point, but you are not performing this because it's very time consuming. Here what we can do, here instead of glycerol we are taking sodium chloride, and you have 1, 2, 3, 4, 5 solutions. So you will be adding sodium chloride in constant quantity of water to produce this final concentration of the sodium chloride. And now all these solutions you will be putting in, note the boiling point for all of them. You will be slowly heating them, and you have you must take digital thermometer, so you could read a correct temperature where the boiling is occurring. So you will simply observe the boiling. When the boiling is going to occur, so you will measure the boiling point, plot the graph between the boiling point and the concentration, and from that plot you have to conclude that how the definition of the boiling point elevation is going to fit. The same way, here you have plotted the delta T D, that is the depression in the freezing point, and in the case of the boiling point you will be plotting delta T F, that is the elevation in the boiling point, again against the molality, and you will be able to calculate not the Kf, it is Kd, that is the depression in the boiling point constant. So that you will be calculating and just trying to evaluate that if you get the straight line or not. So in conclusion, you will be performing just first experiment, and from the first experiment you will plot delta T against the molality to calculate Kf. You already know the value of the KKF, and from the reported value of the Kf, and you should see that what is the experimental error in your measurement. That's all. Any question? Okay, so you will be going into the lab, and when you go in the lab you will be provided with the apparatus, and you should start the measurement immediately. Thank you.
लैब यहीं पे इसी बिल्डिंग में?
हाँ, ये सामने वाली है 102।
मैं सोच रहा हूँ ऐसे ले जाऊँगा इसको।
ऐसे ही लैब में
कितना टाइम चलेगा?
सर 3:30 तक।
मैम कैसे वाले की भी तो नहीं है। हाँ जी मैम स्टार्ट। पूरे
Actually,
थोड़ा बोला ना
Please come forward. If you have any doubt, you can come here. इधर कर देना. So we are demonstrating the depression in freezing point. So you are taking the mixture as in the test tube as per the table which has already been given to you, right? So first of all, like in the test tube 1, so this is test tube 1, we have 12 gram of water and the glycerol is 1 gram, right? So this is the amount which is being taken in the test tube. So now we have another beaker. So in this beaker you will add salt so that the temperature goes below 0 degree. So now you will keep this test tube in this ice bath like this, right? So now you will have a thermometer also, and now you will see when the crystallization will start appearing, and you will note down that temperature. And you will note down that temperature, and you can choose different sets, like a group can do 1 and second set, and the other group can do 3rd and 4th set. So you can choose like this, so that you can do all the readings, because it is very difficult to carry out the whole experiment 8 or 10 readings. So you can carry it out in the sets, first and second set one group, then third and fourth another group, like this. Okay, so this is the first. So first and second we have prepared. So you can take the first and second one group, another group can take third and fourth, and similarly, right? You can pick this one. So what's the crystallization thing?
Actually, what we are going to do. So once we have, you don't need to measure the temperature here. First, you will only see the turbidity. When you see the turbid and turbid solution, take out the test tube, place it in the room temperature. So when the turbidity is gone, the last pinch of the turbidity is gone. At that time, because you will keep the thermometer inside the test tube, and you will know that at the last crystal of the turbidity is gone. At that point, you will know the temperature. Right? So that temperature you have to note down, and that is that temperature and the 0 degree centigrade of water freezing point. So the difference among that is the temperature.
इस वाले मॉडल का प्राइस कितना होता है, मतलब जो कैमरा का बेस है? हाँ हाँ वो नहीं 65 to 70। ये अल्फा मॉडल है क्या? तभी लेकिन पूरा मैनुअल है तो ये ऑटोमेटिक होता है। और ये लेंस का प्राइस कितना है जो एक्स्ट्रा आप खरीदते हैं? ये वाला 51,000 के आसपास है, बट मैंने साला मेन खर्चा जो आता है लेंस के लिए आता है। और सफारी वाले जो लेंस होते हैं जो भारी होते हैं वो कितने के आते हैं?
वो भी डिपेंड करता है अलग कंपनी का।
अच्छा विक्रम सर को तो पता नहीं यार, देखा ही नहीं मैंने। नहीं देखा, पता नहीं बोले
कितना है इनका? माइनस
ਇਹਦਾ ਮਤਲਬ ਕਿਸੇ ਦੋਵਾਂ 'ਚ ਨਾ ਉਹ ਜਿਹੜਾ ਕੰਸੈਂਟ੍ਰੇਸ਼ਨ ਉਹ ਕਿਤੇ ਸੇਮ ਠੀਕ ਹੈ ਨਾ, ਉਹ ਡਿਫਰੈਂਟ ਹੋਣਾ ਚਾਹੀਦਾ ਬਟ ਐਨੀਵੇ ਚਲੋ ਜਿਹੜਾ ਨੈਗੇਟ ਕਰੇਗਾ ਉਹ ਵਿਲ
पहला तो मैंने देखा था बड़ा अच्छा तुम्हारा प्लस में भी है बच्चे? प्लस में है? मेरा प्लस तो आएगा सर, प्लस में गलत है। बच्चे, who is the temperature at which the water will freeze? So if you are adding some matter, it should be depression in freezing point. So at any concentration it should be less than 0. So why it is plus 5? It should be minus
इतना जो हमने गाली दिया सारा
ये तो खराब नहीं होगा, you can repeat it. You can repeat it क्योंकि ये solution तो कोई react नहीं कर रहा ना, तो you can take 2 readings. You can coordinate readings. आप repeat करके रखना, इसलिए आप मिस्टेक जो आई एम फाउंड की कर रहे हो, आप इसमें रख रहे हो, now you have to stir a little bit also, because I think some students they are not stirring it properly. That is why the uniform temperature is not there. Right? So once you stir it, then you will find the temperature. समझ आ गया ना? -2 आ गया, पहले +9 आ
थोड़ी देर देख लो, ये नाम नहीं आता
Sir?
मेरे पे सर्विस करने लगा तो और उनके साथ मेरा एक्सेप्टेंट मतलब क्या बोल सकते हैं लगन टाइम से पता चल जाता है डेट और अरे कुछ नहीं अभी सबसे नेक्स्ट वीक आ जाए कल सुबह कहाँ से यहाँ से काम करना है कंफर्मेशन हो तो कंफर्मेशन ले ले नया कंफर्मेशन अप्लाई करते अगर सब दे देते सर से मैं बात कर लूँगा सर इस डेट पे करा दूँगा
कौन सा अप्लाई बोल रहे ये उस दिन अप्लाई में साथ में कॉल अच्छा आपको कॉल नहीं किया मैंने आज वापस किया ना कैसे आप आपको मैं अप्रोच दे देगा आपको
लेकिन ये इसमें शनिवार फोन होता है शनिवार को हमारा सरकारी छुट्टी पहले 20 दिन के 20 दिन का तो अभी जहाँ पे वीडियो बन रहा है बाकी के बाहर के लोग पर वो नहीं पाएगा नहीं हो पाएगा वो करना तो मैं खुद बोल रहा हूँ अगर ऐसा कुछ होगा शुक्रवार तक हो जाता है बाकी बोल रहा सोमवार
इन सबकी सबकी होगी रीडिंग्स कैलकुलेशन होगी सबकी प्लॉट किया सबने प्लॉट बना लिया सब अपना अपना प्लॉट बना सब लोग अपने अपना Hurry up. Wind up. Students?
So the purpose of our experiment was just to tell you how how we can predict or how we can explain or how we can depict the pressure in the fusion point when we add a solute. So what we have done today, we added glycerol as a solute in pure water, and then we try to find out the freezing point. And what we are expecting, as we increase the concentration of glycerol, and that is what we have seen because we were adding more and more glycerol and we compared the solutions. And by increasing the concentration of glycerol, we expect that the freezing point should be more and more. The magnitude of the freezing point, the pressure is more when we have the high concentration. So we have some fluctuation, and those fluctuations were expected because the concentration we have chosen, they are quite close to each other. But if you have large difference in the concentration, then you have the better accuracy of the experiment. But with the present circumstances or the present kind of apparatus which you have used, the way you have performed the experiment has been fine. Right. So I mean to say that our main purpose was to see how we can actually determine the freezing point of the solution when we increase the concentration that you have already seen. Right. So objectives are well accomplished, and hopefully when we will be having the better facilities and better accuracy, and then you will have clear variation in the freezing point depression with respect to the concentration. So the
One question was from this girl. You can ask him directly.
Sir, what's the role of this freezing point depression and elevation, boiling point elevation in making the nanomaterials gold and silver?
Yeah, this is obviously this is an obvious question because here we are using the conventional solute and the solvent, but in nanomaterials, obviously, you may say that nanomaterials are solute. Obviously, the water is a solvent. As far as my experience is concerned, I never saw any requirement of determining the boiling point of nanomaterial solution. So that is not the objective. The objective is we have to prepare the nanomaterial solution, whether that is a gold nanoparticle, silver nanoparticle, or any other nanoparticle, and we use them for the different kind of applications. If that application needs to be performed at an elevated temperature, then you need to find out that if at higher temperature, if there is any kind of aggregation, because microheterogeneous system, the way we have explained, when you increase the temperature, you increase the randomness of the nanoparticle in the solution. By increasing the randomness, the repulsive interactions usually are overcome by the attractive interactions. So that leads to the aggregation, and that we want to avoid for any kind of application. So therefore, suppose if we have to perform a certain application at 150 degrees centigrade. Okay. So now you have the aqueous solution of gold nanoparticle. Well, what you should do, you need to first check that if that nanomaterial aqueous solution is going to perform the same colloidal property or having the clear suspension at 150 degrees centigrade or not. If before you use that solution for a particular application, you need to check if it is going to, obviously it may or it may not boil at that temperature, but you need to see that by increasing the temperature up to 150 degrees centigrade, or you may say that only 50 degrees centigrade, that is 25 degrees centigrade higher than the room temperature, if that is going to induce any kind of aggregation. If it is going to induce any kind of aggregation, you will not be able to use it for any kind of application. So, bottom line, we don't have any, we are not interested to actually measure the elevation in the boiling point of the gold suspension or the depression in the freezing point, but we need to measure these properties according to the application where we have to use them. If we have to use this nanomaterial suspension of the solution at low temperature, then we will perform the freezing point experiment to see if any kind of aggregation is happening, or if we have to perform the application at elevated temperature. So we will see that by heating the solution, is it obeying the colloidal properties or the rules of colloidal solutions. So as long as they are obeying the colloidal solution, no matter at which temperature you are going to apply for any kind of application, we can use. So that is the objective. But evaluating its boiling point, elevation in boiling point, or the depression in the freezing point probably, that is not that much important. As much we need to see that where we have to use that. You got it? Any other question? Okay, so thank you so much. And now we have to go for our, I think, what's that?
NCAN for inaugural session.
Inaugural. Okay.
So वहीं पे you will have a group photograph. So if you want to order, you can ask directly to the photographer. You will get it on the last day of your course.
And that photograph is compulsory. We have to send it to the ministry. ठीक है ना, अटेंडेंस आपकी उसी से ही ठीक है.
Good afternoon, everyone. We warmly welcome you all at the inaugural ceremony of the GIAN course titled Iron Oxide Nanoparticles for Biomedical Applications Fundamental of Bioapplicability. The term GIAN stands for Global Initiative of Academic Networks, an initiative launched by Government of India to foster international collaboration in higher education. Through GIAN, we aim to bring distinguished experts worldwide to share their knowledge and expertise, enhancing the learning experience and fostering innovations. This platform serves as a bridge connecting academic communities globally and promoting cutting-edge research and education. We have with us Dr. Rajiv Jindal, HOD of Department of Chemistry, Professor Dr. B.S. Kaur, Professor Dr. N.C. Kothiyal, Dr. Jaspreet Kaur Rajput, Dr. Vikramjit Singh, Dr. N.K. Srivastava with us.
We are privileged to warmly welcome the Honorable Director of Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, Professor Dr. Binod Kumar Kanodia, whose leadership continues to inspire and elevate the Institute's academic endeavors. We request Dr. Rajiv Jindal and Dr. Jaspreet Kaur Rajput to honor Professor Dr. B.K. Kanodia. We warmly welcome our esteemed guest, Dr. Mandeep Singh Bakshi from the University of Wisconsin, Green Bay, USA. Dr. Bakshi's expertise in nanomaterial and their biomedical applications will greatly enhance our knowledge. We sincerely thank you, sir, for showing your presence. We now request Professor Dr. B.K. Kanodia to honor our esteemed foreign expert, Dr. Mandeep Singh Bakshi.
We request Dr. Rajiv Jindal and Dr. Jaspreet Kaur Rajput to also welcome the local coordinator, Dr. N.K. Srivastava. We are honored by the presence of all the distinguished experts, faculty members, and enthusiastic researchers gathered here to contribute to and benefit from this course. All of our participations will add immense value to this event, and we are confident that the discussions and learning experience will lead to fruitful outcomes for all. Now, we would like to invite the course coordinator of this GIAN program, Dr. Jaspreet Kaur Rajput, for the welcome address and to put some light on the objectives of the program.
Very good afternoon to everyone. It's my honor and privilege to welcome you all to this session of the comprehensive course titled Iron Oxide Nanoparticles for Biomedical Applications, Fundamentals of Bioapplicability, organized under the prestigious GIAN program. At the outset, I would like to extend a warm and heartful welcome to our chief guest, Professor B.S. Kanodia ji, Honorable Director of the Institute, guest of honor Dr. Mandeep Singh Bakshi, foreign expert from University of Wisconsin, USA, Dr. Rajiv Jindal, HOD Chemistry, Professor B.S. Kaith, Professor N.C. Kotial, Dr. Vikramjit Singh, Dr. N.K. Srivastava, Local Coordinator GIAN, research scholars, staff members and participants who have graced this occasion with their presence. Over the next few days from Jan 13 to 18, 2025, we will embark on a journey to explore the fundamentals and advanced aspects of iron oxide nanoparticles, their synthesis, characterization, surface modifications, unique properties and their promising potential in addressing critical biomedical challenges. Total 12 lectures and 5 tutorials will be conducted in this program. We are privileged to have Dr. Mandeep Singh Bakshi as a course instructor who will guide us through engaging lectures, hand-on sessions and thought-provoking discussions. Me and Dr. Rajiv Jindal will be other two instructors for this GIAN program. So this is a unique opportunity to learn and gain insights into the latest advancements, challenges and trends in this exciting domain. So dear participants, your presence here demonstrates your commitment to learning, innovation and contributing to the future of nanoscience. I encourage you to actively participate, ask questions and network with the peers and mentors through this course. The knowledge and collaborations forged here can pave the way for groundbreaking research and practical applications. Once again, welcome to this exciting learning journey. I hope you find the course insightful, inspiring and transformative. Let us make the most of this incredible opportunity to advance science for betterment of humanities. Thank you and I wish you a productive and enjoyable course.
Thank you, ma'am.
We now invite Dr. N.K. Srivastava, the local coordinator, to share some words on GIAN course. Welcome, sir.
Very warm good afternoon to everyone. Respected Professor Dr. Kanodia, Director, Dr. Mandeep Singh Bakshi, course coordinator Dr. Jaspreet Rajput and Dr. Rajiv Jindal, Professor B.S. Kaith and Professor Kotial sitting on the dais, dear participants and all the students and research scholars of the Department of Chemistry. I welcome you all on behalf of local coordinator GIAN. This is a unique opportunity given by the Ministry of Education to all the participants. There is a live telecast of all the programs running across the country. You can participate in any of the program through that live telecast. But if you have to participate and attend, get the certificate, you need to register for that course. Otherwise, you can freely attend all the lectures and be beneficial from the lectures. We are fortunate that this time total 9 GIAN courses have been approved by the Ministry of Education for the NIT Jalandhar. This is the 5th course which is being organized during this academic year. So I hope your stay during this course will be, because of this inclement weather conditions, it may be a little bit difficult, but if you have any difficulty, you can contact the course coordinators or me during your stay at the institute. I welcome you all once again. Thank you.
Thank you, sir. Now we invite Dr. Rajiv Jindal, HOD of the Chemistry Department, to highlight departmental activities. Welcome, sir.
Honorable Director, Professor Vinod Kumar Kanodia ji, Dr. Jaspreet Kaur, Coordinator, Dr. Nirmal Srivastava, Local Coordinator GIAN, Professor N.C. Kotial, Professor B.S. Kath, Dr. Vikram, and dear participants. It is my honor to welcome you to the inaugural ceremony of GIAN course on iron oxide nanoparticles for biomedical applications, fundamentals of applicability. I welcome Dr. Mandeep Singh Bakshi, Associate Professor, University of Wisconsin, Green Bay, USA, who is here with us as an expert to share knowledge and expertise in nanoparticles for biomedical applications. Dr. Bakshi is here in India since December 16, 2024 to share his expertise with various universities and institutions of Punjab and Chandigarh. It is the top priority of the GIAN initiative to invite the foreign experts to India who could not only deliver lectures for GIAN program but also enlighten the students and faculty in India. This GIAN program is a significant milestone in our institution's pursuit for academic excellence and research innovation. The GIAN initiative, funded by Ministry of Education, aims to bring together renowned international experts and Indian academics to share knowledge and expertise in cutting-edge areas. This program will provide a comprehensive overview of fundamentals of bioapplicability, including the synthesis, characterization, and applications of iron oxide nanoparticles. This program will enhance our understanding of bioapplicability of iron oxide nanoparticles, foster collaborations between Indian and international researchers, provide a platform for young researchers to learn from renowned experts, contribute to the development of new technologies and applications in field of nanotechnology. Over the next 5 days, we have an exciting lineup of lectures, tutorials, and discussions. I encourage you to engage actively in this program. Let me introduce you to our department. The Department of Chemistry is committed to provide a world-class education in chemistry with a focus on research, innovation, and excellence. I would like to showcase our department's achievements, activities, and contributions to the field of chemistry. The Department of Chemistry was established in the year 1989. MSc and PhD programs were initiated in July 2006. Our department has grown significantly with 11 faculty members, 78 MSc students, 40 PhD students on roll, and around 1200 BTech freshers. The department has also been selected as DST Feast Department. Our graduates are equipped with strong analytical and problem-solving techniques, knowledge of modern analytical techniques, understanding of chemical principles and applications, effective communication and teamwork skills. We encourage our students to undertake summer internship in industries, research institutes, and universities. Our students are selected for summer internship offered by SRFP by Indian Academy of Sciences Bangalore, Search by IIT Kanpur, Spark of IIT Roorkee, and Inspired DST. We have dedicated UG and PG labs besides various research labs. During the last year, we have published 5 patents. The Department of Chemistry has completed 12 research projects and 6 more are ongoing. The faculty members are renowned experts in their field and have published more than 800 research papers in reputed journals. The department has conducted 3 GIAN programs so far, 6 national and international conferences. Our curriculum is designed to be flexible so a student can choose courses that align with their interest and career goals. In the nutshell, our department is striving to be a department of academic excellence. I once again thank you all for joining us. Let us embark on this intellectual journey together and explore the fascinating world on iron oxide nanoparticles for biomedical applications. Thank you. Thank you very much.
Thank you, sir. It gives me great pleasure to welcome Dr. Mandeep Singh Bakshi, our esteemed guest of honor, to the podium for his inspiring words and invaluable science. Welcome, sir.
Good afternoon, everybody. First of all, I am grateful to Dr. Rajiv Jindal and Dr. Rajput. So they have gone through a tremendous pressure to submit the proposal and plan the complete course lecture series, and that was really remarkable. And this is second time for me to come to NIT. First time I came here when Dr. Manchanda, our dear professor who left us, heavenly abode, I think probably, I don't remember, probably 3 or 4 years ago. Right? Yeah. So at that time he invited me. I was in Canada at that time. I was teaching in Waterloo. So after that, this is the second time I am here. I probably know most of the people in Department of Chemistry and their research work. This is excellent growth they are doing in terms of research. So Dr. Jindal and Dr. Rajput and their research obviously excellent. And apart from that, Dr. Kant, whom I know right from last 10 years, so he's a very respected researcher throughout the North India. My next generation of professors in IT. So the one is sitting in front of you. So he is our student in GIAN when I was teaching there. First of all, I'm so grateful to Government of India spending such a huge amount of money. You know, I was talking to Dr. Rajput and Dr. Jindal about the amount of the money in dollars. You know, and now I'm teaching in United States. I think from last 10 years. Earlier I taught in Canada 6 to 7 years. From my personal experience, getting this much amount of money in North America from the government of Canada or from United States, it's very hard. Suppose if I'm sending the proposal that I need this much amount of money, obviously the $8,000, that is very tiny amount of money as much as means as far as the University of Wisconsin or other education institutions are concerned in United States, but they have so many restrictions to grant the money. So, but what I have seen that obviously developing country like India, if the developing country like India is spending this much amount of money on the education, so I was so amazed that that my every contribution must be achieved positively by the students. So that was my objective, and that is the objective when we are going to complete this course. I want that I could teach you effectively, clearly, and so that you should have the clear concepts of the material chemistry and how you have to go through the fundamentals, and then how you have to apply the fundamentals in order to achieve the applications which are really required in this part of the planet. So these are actually the focus of this course is on the biomedical applications. So in the course of the lecture C series, so I'll explain that how we can enhance our knowledge, and probably we can generate new ideas. So the bottom line, the main objective of this course is to learn the new aspects of the front areas of the material chemistry, and how we can constructively focus in that direction, and we can produce new generation of scientists. So I want that you must take the maximum advantage from this lecture series, and please do not skip any of the lecture if you really want to achieve something. So therefore, you should attend all the lectures right from the first one. As I told you that my main objective is to start with the basics of the chemistry. Those are very, very required in order to understand the material chemistry, and then eventually I'll walk through the application part. So I want I'll be so much happy if you learn these aspects of the material chemistry and how how we could generate the interest for your future endeavors. So that is my objective. And finally, I must thank again the Government of India as well as NIT and obviously our director and the entire faculty of the Department of Chemistry to achieve the required objectives of this course. Thank you so much.
Thank you so much, sir, for your valuable words. Now I kindly request Professor Dr. B.K. Kanachia, the Honorable Director of NIT Jalandhar, to address the audience. Welcome, sir.
Good afternoon, everyone. So, a very good afternoon to foreign expert, Dr. Mandeep Singh Bakshi, and our faculty members and staff members and research scholars and students and dear participants. I am pleased to welcome you all to this GIAN course on a title Iron Oxide Nanoparticles for Biomedical Application, Fundamentals for Bioapplications, organized by the Department of Chemistry in NIT Jalandhar. NIT Jalandhar has always strived to cultivate the ecosystem of a knowledge sharing and collaboration and bringing academia and industry. Through programs like this, we aim to inspire innovation, equip young researchers with a cutting-edge knowledge and contribute to a solving critical challenge in the science and technology. This event marks a significant step forward in our mission to foster interdisciplinary learning, research and innovation. The field of nanotechnology and particularly the study and application of iron oxide nanoparticle is at the forefront of a scientific discovery. Its immense potential in a revolutionizing biomedical application. So I think that the Government of India is also focused for a biomedical applications. So ranging from a targeted drug delivery system to a advanced diagnostics tools is truly remarkable. This domain not only embody the convergence of science and technology but also represents the future of healthcare. So I think that this topic is very important. Even that our foreign expert, he has also elaborated that how this GIAN course is started and why, what is the aim of this GIAN course. And learning is, I think that our local course coordinator of a GIAN course, he has elaborated that all the GIAN course is online is available. But you can learn of some of a subject in online. But it is a very important that why the physically expert comes from a foreign to here. So there is a interaction. You can learn that we have seen that in a maximum participants, 75% participants from a female participants. So this is a very remarkable in this GIAN course. I have never seen that in a 75% female participant is participating in any GIAN. So even that I asked our professor that how many PhD student research scholar is there. So I think that some of a student is insight or some of a student is inspired with the help of our foreign experts. So you can see that how we can enhance your research in a such a way, so how you can contribute in a world or in a foreign, or you can collaborate of some of a foreign expert and foreign university. You can discuss with our foreign expert. So I think that some of a few of a student is inspired. So I think that our GIAN course is run by the Ministry of Education and Government of India, and you can fulfill the dream of that our young students or young researcher. So I think that our foreign expert has said that the importance of money bring, how the government of India is given the how much money, but if in a case of in a USA or Canada, how this money is bring for a education, it is very difficult. Even that in a registered of a PhD students, I think that professor expert from a foreign university, they discuss that how the project will run, how you can register the PhD student, you will bring up some money from some of industry, then you can run off that your lab. So I think that this is very important. You can learn from a foreign expert. So I thanks the participants who have come from a distance places in this challenging weather to attend this program. I am sure that you will gain valuable knowledge from the session conducted by our renowned experts, and this learning will benefit your study, research and future careers. So let me also take this moment to share some information about our institute, because some of the participants is outside of NIT Jalandhar. So NIT Jalandhar is spread over of 154 acre and is a home to more than 6,000 students. Our institute is known for its academic and research excellence and hold commendable positions in a national and international ranking. This year our faculty has published more than 1,155 research papers in a reputed journal, contributing to the institute edge index of 107, which reflect the quality and impact of research contribution. Our faculty members are engaged in an ongoing research project worth of more than 45 crores and have a completed consultancy project worth of 5 crore in a past year. The institute has also awarded 3 FIST projects. Even that Professor Jindal has discussed that how the FIST project is a chemistry department has engaged, but currently we have awarded of a 3 FIST project in a total worth of 5.5 crores and established 2 center of excellence in a 5G and beyond and cyber security. With a strong placement record of around of 90% and highest package of reaching of 52 lakhs, NIT Jalandhar continue to focus on academic excellence and career development. To nurture creativity, innovation and entrepreneurial skill, the institute has established a technology business incubation TBI and Space Technology Incubation Center STIC funded by ISRO. Recently, the institute signed MOU with the IIM Visakhapatnam for a dual degree program enabling students to pursue a MBA degree online from IIM Visakhapatnam while completing their degree program at NIT Jalandhar. As part of an infrastructure development, grant of rupees 240 crore has been sanctioned under a HEPA for the construction of a 2 state-of-the-art academic block, hostel and residential facility. So I once again thanks our foreign expert, the course coordinator, local GIAN course coordinator and department and all participants for making the program a success. I wish you all the great learning experience and fruitful program and discussion. Thank you and my best wishes.
Thank you so much, sir. Now, I sincerely request the course coordinator, Dr. Jaspreet Kaur Rajput, to deliver the vote of thanks and express gratitude to all who made this event a success. Welcome, ma'am.
It's my privilege and honor to extend a vote of thanks on the behalf of organizing team. First and foremost, I would like to express my heartfelt gratitude to our foreign expert, Dr. Mandeep Singh Bakshi, for accepting our request to be an instructor for this GIAN course. We are deeply grateful that you took the time and effort to join, traveling from US to here. It reflects your dedication to fostering international collaboration and knowledge sharing, which we believe are critical in today's interconnected world. I am privileged to extend my gratitude to our esteemed director, Professor B.S. Kanodia, for his invaluable presence and support. Sir, your unwavering leadership and vision have always been a guiding force for us, so it reinforced our commitment to strive for excellence. I would like to express my thanks to local coordinator GIAN, Dr. N.K. Srivastava, for helping us in organizing this course. I would like to extend my heartfelt thanks to the organizing team, sports staff, and especially the research scholars who have worked tirelessly to make this course a reality. Your dedication and the hard work are what make this such academic endeavor successful. My dear participants, we appreciate the efforts and enthusiasm you show in joining this course. Over the next few days, we hope you find the sessions insightful, the discussions enriching, and the overall experience both inspiring and rewarding. Thank you, and I wish you all fruitful and engaging course.
Thank you so much, ma'am. I kindly request all our esteemed guests and the audience to please stand for the national anthem.
अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you everyone for your presence, and we look forward to insightful discussions and meaningful learning experiences throughout this program. We are delighted to invite all our esteemed guests and participants for the refreshing tea and snacks, followed by the group photograph.